Good morning to everybody. We greet our participating authorities in this opening ceremony. Dr. Román Linares Romero, Director of the Division of Basic Science and Engineering, whom we also thank for the financial support for the publications of the proceedings of this symposium in the Revista Mexicana de Física. Dr. Jorge Garza Holguín, Head of the Department of Chemistry, who for health reasons cannot accompany us, but we thank all the willingness and support for the successful planning of this event. Dr. Juan Morales Corona, Head of the Department of Physics, and Dr. J. Raúl Montes de Oca Machorro, Head of the Department of Mathematics. We also thank both of them for their good disposition towards the symposium. Also to Dr. Rodolfo Esquivel Olea, Head of the Quantum Chemistry Group. To Dr. Roberto Quesada Batalla, we thank his participation on behalf of the Head of the Department of Mathematics. When we started planning this event, we did not imagine the great interest it will arouse in the scientific community that cultivates this research topic, so that what we originally thought will be 2 days of conferences turned into 4. It is a pleasure to be here on the occasion of celebrating the 58th anniversary of the Autonomous Metropolitan University, la Universidad Autónoma Metropolitana, from this scientific trench. For this interest, we thank all of you, participants and attendees. We will give the floor to Dr. Román Linares, Director of the Division of Basic Sciences and Engineering. Please, Professor Linares, the microphone is yours.
Thank you very much to the organizers for this invitation. Okay. And I will read my brief speech. Esteemed colleagues, distinguished guests, and participants. It is with great honor and enthusiasm that I welcome you to the Conference on Application of Information Theory in Natural Sciences. This event brings together researchers from different disciplines to explore the profound impact of information theory in a wide range of scientific disciplines. As we celebrate the 50th anniversary of the Universidad Autónoma Metropolitana, we reaffirm our institution's dedication to advancing scientific knowledge through interdisciplinary collaboration. Over the years, the UAM has fostered a rich research environment where theoretical and applied science converge to address fundamental and contemporary challenges. Information theory, since its origins with Shannon's groundbreaking work, has become a cornerstone of modern science, shaping how we understand communication, complexity, and structure in natural systems. Its applications range from quantum mechanics and statistical physics to computational biology and artificial intelligence. At UAM Iztapalapa, information theory is not a new endeavor. Several colleagues have been working in this field for many years, producing a significant body of research and contributing to its development across multiple disciplines. Our faculty's sustained effort has led to numerous scientific publications and a growing engagement with information theoretical approaches in our research community. The abstracts presented in this conference showcase the diversity and richness of current research in the field. Topics such as entropy in thermodynamic systems, information theoretic methods in quantum mechanics, and their relevance in neural networks and complex systems highlight the breadth of this discipline and its potential for further exploration. Moving forward, there is a great opportunity to strengthen and expand research and information theory at UAM Iztapalapa. By fostering interdisciplinary collaborations and encouraging the active participation of undergraduate and graduate students, we can continue to position this field as an integral part of our scientific development. The enthusiasm and engagement of young researchers will be crucial in shaping the future of information theory within our university and beyond. I extend my deepest gratitude to all the speakers, both national and international, for sharing their expertise with us. Your contributions are invaluable, and I am confident that the discussions over the next few days will spark new ideas and collaborations. Let us take full advantage of this conference to exchange knowledge, challenge ideas, and inspire future research. welcome, and I wish you all a stimulating and productive event. Thank you very much.
Okay. Thank you very much. I think is working? Okay. Thank you very much, Professor Linares, for these words. I think that it's important to mention that in our university that we are celebrating 50 years of existence. There are people from the Department of Chemistry, Physics, and Mathematics who cultivate the development and applications of information theory in many different fields. We will then give the floor to Dr. Rodolfo Esquivel, who will give us a few words on behalf of Dr. Jorge Garza, the head of the Department of Chemistry, who, as mentioned, for health reasons, is not here. Please.
I got it here, no problem.
Yeah.
Thank you very much, Humberto.
Thank you so much.
Well, on behalf of Professor Jorge Garza, head of the Department of Chemistry, who is unfortunately unable to attend today, but he expressed a message for us. I extend our sincere gratitude for the enthusiastic participation of specialists from various institutions. We thank our colleagues from UAM, Basic Sciences, and Engineering departments, as well as participants from several Mexican institutions, including Universidad Nacional Autónoma de México, Instituto Politécnico Nacional, Benemérita Universidad Autónoma de Puebla, Universidad de Guadalajara, and also from a private company. We are also honored by the international participation from universities across the world in the United States, Spain, United Kingdom, France, Germany, Hungary, Argentina, India, and Greece. Information theory sciences, along with quantum technologies, have established themselves as crucial research focus at our university, UAM, spanning both basic and applied fields. The Quantum Chemistry Group has been at the forefront of information science since the early 1990s, incorporating its research into both our graduate and undergraduate programs to shape the academic journey of many of our students. We take pride in acknowledging the Quantum Chemistry Group's significant contributions to this field, particularly today, by organizing this important event, Applications of Information Theory in Natural Sciences, as part of the academic activities commemorating the 50th anniversary of the Universidad Autónoma Metropolitana. I wish you engaging discussions and a productive conference. Thank you all for participating. Professor Jorge Garza. Thank you.
Thank you very much, Rodolfo. It's a pleasure to give now the floor to Dr. Juan Morales, the head of the Department of Physics. Please go ahead, Professor. Thank you for being here.
Thanks. Okay. Good morning, ladies and gentlemen, honorable integrants of the Presidium. Dr. Román Linares Romero, Director of the Division of Basic Science and Engineering. Jorge Garza Holguín, Head of the Chemistry Department. Roberto Quesada Batalla, Dr. Roberto Quesada Batalla, representing of Raúl Montes de Oca, Head of the Mathematical Departments. Dr. Rodolfo Esquivel Olea, Head of the Quantum Chemistry Group. Dr. Humberto Laguna Galindo, Chemistry Department. Thanks for the invitation to this event. It's an honor for me address to you on behalf of the Physics Department in the Symposium of the Application of Information Theory in Natural Science. With the quality of the talks that we presented, I confident this be an outstanding event. The goal of this symposium is to foster collaboration among research whose work in related to information theory and its application in natural science. The program for this 4 days to work demonstrate international interest, given the nationality of the participants. These topics in information theory are being cultivated in various departments of the UAM Iztapalapa campus. This event aimed to undergraduate students and graduate students, as we as specialists in chemistry, physics, mathematics, and related or emerging science. It also seeks to disseminate recent advances in quantum technology. Information theory is natural science, serves a bridge between disciplines, enabling to unravel the mystery of the nature. For example, tools such as on information entropy and early tools, information entropy in confined quantum system, or a model energy transport in photosynthesis are part of this meeting. And all lecture or talks are very interesting. Now, more than ever, we must embrace the interdisciplinary perspective. The integration of information theory into natural science not only helps to understand the world, but also equips to address global change, such as diversity, conservation, climate change, and understand our own biology. Thanks.
Thank you very much, Professor Juan. It is really a pleasure to be here in this multidisciplinary event. So the next participation is for Professor Roberto Quesada, who is representing the head of the Department of Mathematics. He was unable to join us because another academic event with students. I think that Professor Roberto Quesada is in the Zoom session, so maybe Professor Roberto, you can start your audio, I think, and your video if you want. Okay, now we see you. Pero no lo escuchamos. Wait a minute, please, Professor. Okay. ¿Y este lo apago? Yo lo apago desde acá. Okay. Yes. Yes, we can hear you.
So, it is my great pleasure to congratulate the organizers of this symposium on information theory and application. In our Department of Mathematics, there exists a line of research on quantum Markov Semigroups, which has important connections in probability and also with quantum physics. In particular,
head of the quantum chemistry group of this chemistry department, and on behalf of the organizing committee, will give us a few words. Please go ahead, Professor Esquivel.
Thank you very much, Humberto. Good morning, distinguished guests, speakers, and participants. It is my great honor to welcome you to the Symposium on Applications of Information Theory in Natural Sciences, a gathering of pioneering researchers from diverse fields, united by the shared goal of exploring the intersection between the information theory, quantum technologies, and natural sciences. As we embark on this exciting journey, allow me to briefly outline the key themes and contributions that will define this symposium. We begin by examining the foundational role of information theory in science, exploring concepts that entropy, like statistical mechanics as unifying frameworks across physics and chemistry. These discussions will illuminate how information theory connects quantum mechanics, thermodynamics, and relativity, providing fresh insights into the foundational principles of nature by speculating on how information might bridge quantum physics and general relativity. We take steps towards envisioning a new unified theory of physics. Building on this foundation, the symposium explores quantum systems and correlations, where concepts such as quantum entanglement and information theoretic measures redefine classical notions like chemical bonding and electron interactions. These explorations deepen our understanding of quantum phase transitions and topological properties, bridging abstract theories with observable behaviors. Among these contributions, the intersection of information theory and experimental physics takes some particular significance. For instance, using Bose-Einstein condensates as experimental platforms to probe the intersection of quantum mechanics and relativity stands out as a visionary approach. This line of research addresses fundamental questions about the nature of spacetime, showcasing the ability of quantum systems to investigate realms otherwise inaccessible. The symposium also highlights interdisciplinary applications and technologies, where information theory seamlessly integrates with other fields to solve complex problems. A striking contribution involves applying chaos theory and multifractality to better understand natural systems. These approaches reveal hidden patterns across scales, demonstrating the versatility of information theoretic tools in characterizing dynamics and chaotic processes. Such efforts exemplify how abstract measures can decode intricate systems and their real-world applications. On the chemical frontier, the symposium provides solid perspectives on chemical reactions and molecular structures, where information theoretic tools shed light on concurrent processes of reaction pathways such as bond breaking and bond cleavage energy reservoirs, which are inaccessible from other theories. These methods push the boundaries of theoretical and applied chemistry by uncovering deeper patterns in molecular behavior. Finally, we explore the experimental and practical frontiers, showcasing how theoretical advancements translate into real-world applications. Topics such as turning quantum entanglement useful for precision in metrology and quantum technologies underscore the transformative potential of these ideas. These discussions demonstrate the crucial role of experimentation in turning abstract theories into impactful innovations and highlight the collaborative spirit required to bring such advancements to life. Reflecting on these diverse contributions, one thing becomes clear. Information theory serves as a universal language, bridging disciplines and enabling novel approaches to some of the most complex challenges in science, from understanding quantum entanglement to unraveling the intricacies of chemical reactivity. This symposium underscores the remarkable power of collaboration and innovation. It is this collective spirit that makes events like this so impactful, by bringing together expertise from across disciplines. We not only share knowledge, but also inspire one another to push the boundaries of what is possible. These efforts remind us that through collaboration, we can unlock new opportunities for discovery and progress. Thank you all for being part of this journey. I wish you an inspiring and fruitful online gathering, filled with insights, connections, and opportunities for meaningful collaborations. I will also take this opportunity to express my deep gratitude to the members of the organizing committee, Robin Sagar, Humberto Laguna, and Carlos Salazar, for their dedication and enthusiastic participation in organizing and coordinating the logistics of this event. Our gratitude also to Jorge Garza, head of the Department of Chemistry, and Roman Linares, director of the Division of Sciences and Engineering at UAM, for their support. Well, finally, it is now my pleasure to introduce our first guest, Vlatko Vedral, from the University of Oxford. Professor Vedral is worldwide known as a science communicator and a leading expert in the field of quantum information science. At this point, I would like to share an anecdote with you. Some time ago, I had the privilege of meeting Vlatko at the Carmen de la Victoria in Granada, who is in front of the Palace of la Alhambra, a beautiful university facility for scientific gatherings. During that visit, he graciously signed a copy of his book, Decoding Reality, this one here, for me. With a touch of humor, he added this dedication in my book. I'm going to share it to you. To Rodolfo, with all my entanglement. He warned me not to misunderstand it. Of course, I didn't. And I thoroughly enjoyed reading such an enlightening book. Thank you, Vlatko, for that moment and for joining us today. It is in the same spirit of connection and collaboration that we warmly welcome you on behalf of the organizing committee with all our entanglement. To that, we are confident it will be a successful and inspiring event. Before we proceed with Professor Vedral's talk, a quick logistical note, please. Given our tight schedule, this will not be a Q&A session immediately following any of the talks. However, we have set up a WhatsApp discussion group where you can post questions and forward them to the speakers, hopefully in the spirit of collaboration. Now, I don't know, well, Professor Vedral will be ready.
I think yes, he's here in the session. So let me say that I will copy and paste this link at the
Yeah,
chat.
the WhatsApp link.
Yes, the
Okay.
WhatsApp link, and let's give a few last words to acknowledge our colleagues, and let's thank the authorities of the university. So let's start with the. Thank you very much, colleagues. Thank you very much, Rodolfo. So let's start with the science of this symposium. Thank you for the in-person and Zoom audience. So, go
Okay,
ahead.
now it is my great pleasure to invite Professor Vedral to begin his presentation. Vlatko, you have 45 minutes to share your thoughts and inspire us with your insights. Anytime, Vlatko. Ah, está. Muchas gracias. Muchas gracias.
Hello.
Excellent. You can hear me?
Yes, we can
Yes.
hear you. Thank you.
Perfect. And you can see the slides, I'm hoping.
Your slides.
Brilliant. Rodolfo, it's a great pleasure, and I'm very grateful to the organizing committee as well to give me this opportunity. I'm sorry that it's not in person. I'd love to visit, and I will do that at my earliest opportunity. So I had the luxury of being the first speaker, which means I will make it very simple and it will be more like an overview of, with the, of course, of personal twist into the role of information in quantum physics. But I want to say something towards the end, which I think will become increasingly more and more important for us. So to zoom out first, physics, of course, has always used the notion of information, even informally, not necessarily very formally. But as we all know, the main goal of a physical theory really is to formulate the tightest description, the most consistent description of the phenomena that we observe around us. And in that sense, the information that you have about the system is extremely important, even in classical physics, of course, not just in quantum physics. And here I'm mentioning the two, there are more, but there are the two well-known demons that we always use in classical mechanics to illustrate certain features, even of Newtonian physics. So Laplace, of course, says if I have all the information about the positions and momenta of all the particles in the universe, then of course Newton's laws tell me deterministically exactly what's going to happen in the future. Maxwell, on the other hand, uses the same information, but what he was really worried, so Laplace was worried about determinism. In fact, I don't know if he was worried. Maybe he thought that this was a great feature. Whereas Maxwell was worried that actually if you have exactly the same information as Laplace, you can actually violate the second law of thermodynamics. And I think this interface between physics information and thermodynamics has been extremely fruitful even in quantum information. So the field of quantum thermodynamics capitalizes a lot on this. But what I want to say is I want to continue with this logic that physics is all about information, really, ultimately. And I'm using the phrase that I took directly from Schrödinger. He talked about quantum states as catalogs of information, but in fact, we can talk about, even in terms of Laplace's and Maxwell's demons, we can talk about states of physical systems as some kind, I'm now borrowing the language of gambling, if you like. We can think of them as betting portfolios. So the state simply presents the best information we have that we are going to use about betting on the future states, if you like, of the outcomes of various experiments that we will perform. And the laws of physics, and I think this is a very fruitful metaphor, if you like, and not just a metaphor, the laws of physics, of course, tell us how this portfolio should be updated as time passes on. So if we were to bet in half an hour, how should we actually manipulate this initial information and update it in order to get the best possible description? And of course, the key difference in quantum mechanics is this notion of a quantum bit. That you can bet on different things in quantum mechanics, but of course, unlike in classical information where you are only talking about classical bits, about zeros and ones, one at a time, if you like. In quantum physics, you have this concept of a superposition. So, of course, you can use this simple example of a photon going through a beam splitter or any other such event in the microscopic world. You can use it as a definition, almost as an encoding of a bit, because if detector 1 clicks, that represents a logical 1. If the detector 2 clicks, it's a logical 2, if you like. But of course, we can also make a superposition. So we don't have to encode information in the zeros and ones. In the basis states, we can actually encode it into the phase of the system. And in fact, there are infinitely many ways, even for a single qubit, to decide which degree of freedom, which quantum number, which observable, if you like, should carry that information. And so that's the main thing. Now, when it comes to the measures of information, what's been extremely useful to us in physics in general, but in particular in quantum physics,
is, of course, Shannon's notion of information. And he said he stripped information of all the unnecessary noise and anything else that basically is redundant. And he said it all boils down to understanding probabilities for various things to happen. And once you have a probability, you can quantify information by using this formula that it's a log of 1 over the probability. So the less likely something is, the more information this carries if it happens. Of course, a physicist won't be surprised to see this. Boltzmann obviously arrived at a very similar conclusion. I don't think he was thinking about communicating information from A to B, but of course he was thinking about thermodynamical entropy and explaining that. This already tells you in many ways that in class, and here is maybe the punchline about quantum mechanics, which distinguishes it from classical physics. In classical physics, as we saw from Laplace, something either happens with 100% probability or it doesn't happen. It happens with 0 probability. So determinism in classical physics, providing that you have all the initial information, and of course classical physics doesn't prohibit you from having this. Basically in classical, if you apply classical information theory to Newton, then it becomes trivial in the sense that exactly in the sense that there is no notion of probability unless, of course, you are introducing coarse graining, you are deliberately losing information, it's a lack of information, and so on. But these are all, in a way, subjective. In the final analysis, if you do have all the information, and in principle you could, the probability vanishes, if you like. It's either 100% or 0. Whereas in quantum mechanics, because of this property that we can encode classical information in infinitely many different quantum numbers, even for a single qubit, this automatically leads to the uncertainty principle. So each of these directions, each of these observables, as we call them, I prefer to call them Q numbers, like Dirac, each of these quantum numbers is a good enough classical carrier of information. But put together, they don't constitute classical information. They go beyond classical information. And it's precisely because if you specify the bit in one direction, you're automatically uncertain as to the value of the bit in any other Q number. Anything that's complementary doesn't have the classical information determined in the same way. And this, of course, justifies that's why some people say probabilities are randomness, uncertainty, whatever you want to use to quantify this, in fact, is fundamental, is intrinsic to quantum mechanics. You cannot avoid it. And it seems, therefore, that the Shannon logic for information becomes fully operational, really only with quantum mechanics. And like I said, already Schrödinger was alluded to the fact that quantum physics is a form of information theory. This was before Shannon. And so the key feature, of course, is entanglement ultimately. And I think to me, our understanding of quantum mechanics has really improved a great deal after we started researching into quantum information. So it's a kind of like a lens. You can zoom out and look at the key features. And I think the key features are always really information theoretic in origin, that somehow compares different theories and discriminates one theory from another one. And I will have something to say about it in about 10 minutes time as well. But Schrödinger, he wrote 2 papers in 1935, one in German and the other one in English. He was bilingual. And basically, in one of them, of course, it's the famous cat paper, Schrödinger's cat paper, but in the other one, he actually mentions quite a lot of things that ultimately become used in quantum information, like the steering. But look at the way that he even expresses the concept of entanglement, that somehow he says the information about A and the information about B separately is not the same as the information about A and B together. So these catalogs of information, as he called them, you can actually write down, and I think all of you know this, if you're familiar with quantum mechanics, you can write down the catalog of information for A and B together. But in fact, if you look at them separately when they're entangled, suddenly their states are mixed. You can no longer call them pure catalogs of information. And Schrödinger notices all of these things. Like I said, this was prior to Shannon and all of the other later developments, but all of this is already contained in his 1935 writing. What attracted me, incidentally, I said this was going to be a little bit more personal because most of my research has been really in quantum information, and I think I've benefited enormously from information theory, and I think we will benefit even more. In fact, I want to finish the talk by telling you about the next 10 years in physics. But what attracted me is the experiments. This is just one of them. Lots of these experiments are of a very similar kind. But this is cavity QED. These are the Nobel Prize winning experiments that Arosh and his colleagues were doing in the 90s, in fact. And the picture I borrowed from one of his later articles, may even be the Nobel lecture, actually, I'm not quite sure. But what he does beautifully is he uses atoms, which he prepares at this point B, then prepares them. I don't want to bore you with the details of this, prepares them through these what we call Ramsey pulses. It's not really relevant, but the main point is that the atoms then interact with the light inside this cavity C. So in order to probe the features of light, you use atoms that entangle themselves to light. And in order to prepare atoms to understand the state of the atoms, you use the light in the cavity. And I think this is a very important message. And again, Schrödinger was fully aware of that, and many other people. That entangled state, you can think of them as basically the concept, embodying the concept of quantum information, where when two systems become entangled, it's completely irrelevant which of them observes which other system. And to me, this is one of the main messages of quantum mechanics, that there is no distinction between the observers and the observed. I think this is one of the very common misconceptions, and many physicists, many quantum physicists make it, I think, and it's very unfortunate. But in fact, I think the main message in quantum mechanics is there are no observers. There are no special observers, if you like. Observers are just other quantum systems. Now, obviously, when you talk about information as a form of correlation in general, this is also not unique to quantum physics. In fact, in many body physics, in classical solid-state physics, if you like, lots of things are based on the notion of correlation. And I want to contrast this one just for about 2 minutes now with what we just said about Shannon. It's not the same kind of information. It sounds like it ought to be related, and it certainly is related, but I just want to warn you that it's not quite the same concept. So in physics, we talk frequently about, for instance, spin-spin correlations in a chain of spins. How does it decay as you take the spin separation to go to infinity, for instance? And what I'm saying here is that this is something that we would call a disordered phase, when the correlations between spins, let's say when you're characterizing magnetic properties of the system, when the correlations go down to zero rapidly, exponentially rapidly, we usually think of that as a disordered state, not a magnetic state, if you like. And similarly, we can talk about, for instance, Bose condensates, and we can talk about being below the critical point, in which case you have the correlations of the type that I wrote down here, which are just the number correlations. Look at the mode A, look at the mode B, look at how particles are correlated between these two, and if they're not correlated, you are basically not in the critical regime. And there's a host of other things. Of course, I don't want to bore you too much, and it would take us too far from the message that I want to communicate, but I've written quite a lot about it. For each of these topics that I'm telling you about, there is almost a reviews of modern physics that I've written on that, and I've probably exhausted quite a lot of it that I want to say here. And of course, there's a connection with entanglement here. But here is exactly where my warning comes in. What a solid state physicist would call a highly correlated system, which is this first state that I wrote down. Each spin points in exactly the same direction. So you could think of this as an ordered ferromagnetic phase, as we learn in the undergraduate physics. However, for an information theorist, for Shannon, for us here, in fact, for me, this would be considered an uncorrelated state. And Schrödinger certainly would have agreed with this. And the reason is that if you look at Shannon's mutual information, which is basically the entity that he used as a capacity for his communication, if you look at the definition of this, it says take the entropy of the subsystem A, add the entropy of B, completely symmetric, and then subtract the total entropy. And if you look at any product state, spin up, then the entropy of each of the spins is 0 because they're in a pure state. The total entropy is also 0 because it's a pure state overall. Therefore, this measure, mutual information, gives you 0. So it's not correlated. For something to be correlated, there's got to be some kind of uncertainty in each of the subsystems. If you don't have that, you don't have correlations, according to Shannon. And I think that's a better way of talking about correlations and about information. So here are two very simple examples. If you have something that we would just call a classically correlated state, I write it as a quantum state, but actually is a state which is a classical mixture, if you like, no phase between the two, of spins pointing up with 1/2 probability and spins pointing down with 1/2 probability. According to Shannon, this has 1 unit of correlation. And in fact, that's maximum you can get in classical physics, in classical information theory. And the beautiful thing about entanglement, and that's where all of this research that was developed possibly in the mid and late 90s actually comes in, is the fact that if you have an entangled state, and I think Schrödinger verbally anticipates this, he doesn't quantify it this way, but effectively it's clear that this is what he means, is that if you take a maximally entangled state, what we call a Bell state, where the spins are pointing simultaneously up and down with an equal amplitude in this case, this, according to Shannon, has 2 units of information, 2 units of correlation. And that's interesting, twice as much as the maximum you can have classically. So this already anticipates lots of things like Bell's inequalities, that correlations quantumly ought to be, at least for some states, ought to be higher than anything allowed classically. So this extra 1 unit of mutual information is exactly in this case because of entanglement. I wrote a lot about it. This actually using relative entropy to quantify this, which is another information theoretic tool, was my PhD thesis really. And it took me a few years that someone in fact invited me to submit it to the reviews of modern physics, and maybe that's the best place to read about it if you want to see what happened at that time. Now, very briefly, to tell you the summary of lots of these things, what you have to discriminate in quantum physics are the quantum correlations, entanglement, from the correlations that are partly quantum, partly classical, and these are these separable states that I wrote down. And then way down, if you are degrading the concept of information, you encounter classical correlations. And of course, even below that, you encounter states that are not correlated at all. And so the game for a long time has been to really investigate the meaning of these states, how to characterize them, how to quantify them, and how do they link to physics? In fact, what it is that we can do with different states in terms of information processing, but also do they tell us some extra things about different phases of matter, about quantum thermodynamics and things like that. And again, I don't want to bore you with these things we've developed all sorts of ways of understanding how to characterize different states. Possibly this slide is more useful than the other one. That, as I said, just summarizing with 2 subsystems, but the story generalizes to any number of subsystems. We are trying to discriminate states that are not of this form, which are basically called entangled. They're not of the separable form, from the states that are separable, which, like I said, locally contain quantum description. These row A's and row B's are in fact density matrices, so they're still quantum. They still allow superpositions to exist at the individual level of subsystems. But when you put them together, you are simply using not an amplitude, but a classical probability distribution to mix them, if you like. And so these states can do something for you. It's not that they can't do quantum information, but what they can do is much more limited than what you can do with entangled states. And of course, now we are in this intermediate regime with quantum technologies, so people are investigating how far can you really beat classical algorithms even with states like this. And then, as I said, as you slide down, as you destroy more and more information, you encounter states where you really have distinguishable you have a basis for subsystem A, it's correlated to the basis for subsystem B, so you're literally sticking to only one basis. It's like classical information. And these are just classically correlated states at best, or they're product states as I wrote them down. Maybe they're not even correlated. So this is a crude kind of division of different correlations in a quantum state. So either they're entangled, or they're separable and they contain what we call quantum discord, or they don't even have discord, in which case they're just classically correlated, or they're not even correlated at all, in which case they're simply product states. And again, I have yet another. If we didn't have this pressure to publish short papers and glamorous papers every once in a while, I think I'd be only writing reviews of modern physics. It makes, it's far more enjoyable to think about something properly and then, spend a few years and put your thoughts down into that. And so there is, like I said, for each of these topics, I have a RevMod quiz, I think, to tell you a bit more about it if you want to. So this is maybe a picture of the state of affairs, again, very crudely. And maybe one thing I want to say here at this point, and I'm happy to talk more about it if anyone is interested, is that all of these things that we've been developing for spatially correlated quantum bits, now there is actually a subfield emerging which is translating this into time. And I think this to me is extremely interesting. Like I said, I won't be able to tell you more than just one sentence now. But what does it mean to have a mutual information? What does it mean to have quantum correlations, entanglement in time? After all, in physics, as you know, we're all about, relativistically speaking, treating space and time mathematically. They're not the same, obviously, but they transform into one another when you go from one observer to another inertial observer. And so somehow our description should reflect this. And the question is, what does that mean for the notions of correlations that we've been developing for spatially correlated qubits? What about a single qubit, for instance, at 2 different instances in time? I think this is, like I said, this is a very interesting emerging topic. And I think we'll get quite a lot of mileage out of it as well. And so now the point I want to make, actually, which is really the last bit of my talk, is the following. I think that quantum information is not that it's just improved our understanding of quantum mechanics. It certainly did. Certainly has led to these highly promising technologies, and you know that everyone is excited about it, everyone is investing, everyone has a startup and all sorts of things like that. But what really interests me as a physicist always is information going to help us make another breakthrough in physics? Does it tell us anything about what kind of things we should be doing in order to test for the future physics? And actually, my claim is that the answer is yes. In fact, I'm finishing another book on this topic, how quantum information will help us get out of this conundrum of quantizing gravity, and I will get to that. But let me set the stage for this. So the ultimate way of thinking about information in quantum mechanics is really always to think in terms of waves. That the universe, and this of course is reflected in quantum field theory, that everything is a wave, everything is a field. But what quantum really means is that the properties of these waves are not classical numbers like in classical waves, you know, the height of your wave, the phase of your wave, if you like. These are the complementary observables, and they can be known arbitrarily well in classical, let's say, wave optics, for instance. However, quantumly, what it means is that each of these becomes a Q number. It's an operator, it's a matrix, and therefore you cannot specify them simultaneously. And so these Q numbers are really responsible for all the quantum effects that we discuss. The uncertainty principle, the superposition, even leading to quantum entanglement. And I want to spend a few moments on this because I think viewing everything as this kind of quantum waves interacting and exchanging quantum information is the right way to think about this. And in fact, the reason why we encountered many stumbling blocks, in my view, is because we are not taking this view holistically. It should really apply to everything. I'll take you back over the next 2 minutes through one of the initial problems as it was perceived by the researchers in the late 20s, 1920s, 100 years ago, which basically after the advent, Heisenberg and Schrödinger, you know, the matrix and the wave mechanics, people said, well, wait a second, if particles really are waves, and that was de Broglie, obviously, the de Broglie hypothesis, then why do we, when we do experiments like this one, detection of alpha particles in a cloud chamber, why do we see tracks which look ridiculously classical? Actually, they look Newtonian. Each of these alpha particles goes in a straight line, basically. Why, if the claim is that an alpha particle is a wave, why don't we see something like this? So this is a big problem. There are pages and pages of the transcript discussion of the Solvay, the famous 1927 Solvay meeting, where basically they're all discussing this issue. What does it mean for particles? What does it mean for everything, not just particles, to be waves? That's the underlying picture. And in fact, what emerges here, and this is, I think, where quantum information took this on board seriously and really capitalized a lot on that. And all of these things to do with entanglement swapping, teleportation, dense coding, all of them are really an outcome of this kind of thing. So there's a chain of people there that, in my view, contributing to clarifying this. It starts with Heisenberg. He's got a beautiful discussion of this. Then Darwin, Charles Darwin, the grandson of the biologist Charles Darwin. He was a physicist himself, Charles Darwin. Mott, finally, I think, writes a definitive paper on this. And later, Schrödinger also acknowledges it. So basically, what they all say is that when this part, it introduces the notion of decoherence for those that are familiar with this language. So in each run of the experiment, the alpha particle does spread like a wave. However, it's sitting in this cloud chamber of molecules, and each of these trajectories is basically just ionization of the molecules as they get hit along one branch, and then they condense, they vaporize other basically molecules around them. A little bit how an airplane leaves a track in the sky. It's more or less the same physics that leads to these tracks that really, if you zoom in, are discretized bunch of bubbles that the particle leaves in its wake as it propagates. But in fact, what all of these people concluded is that the particle really does go in all directions. And for each of these tracks where you get condensation along that track, there are all the other tracks where you also had condensation along the other ones. There's no reason to think that they don't also exist in this entangled state. This is exactly like your Schrodinger's cat experiment, or one instance of Schrodinger's cat. In fact, this kind of experiment led Schrodinger to write about entanglement. And what I think, usually we associate this with Everett, but I think there's a whole history behind it. And I think Schrodinger, a year or two before his death, in fact, delivered lectures that were published much later in Dublin, I think, where he outlines this picture of the universe. So the measurement is just a creation of entanglement between two systems. And like I said, in this picture, there is no distinction between the observer and the observed. Each measures the other one. You can say that the alpha particle measures the molecules in the gas, and at the same time, the molecules measure the alpha particle. It's completely symmetric. The quantum description doesn't allow you to make one of the two more important than the other one. And what Schrodinger loved, by the way, here is the thing that actually the new book I'm writing is exactly there to exercise all of these kind of things that people are still discussing, and I don't think they're problematic anymore. So Schrodinger says, if you take this view that it's just waves coupling to one another, quantum waves, Q waves coupling, then there are no collapses, there are no quantum jumps, there are no discontinuities, there's no spooky action at the distance either. The spooky action emerges only because you're trying to enforce classical description on something that's intrinsically quantum. And that's beautiful. So that's kind of, that encapsulates this view that it's only if you view everything through quantum physics, through quantum information, that it becomes ultimately consistent. In fact, and this is usually back to front, even how we teach quantum mechanics, I'm almost there. In fact, even classical physics owes its existence to entanglement. So it's not, so the way we teach quantum mechanics, of course, and maybe pedagogically this is the right way, although I'm not so sure myself. The way we teach is that we start with the classical description. We start with classical Hamiltonian, classical energy, and then we put hats on the relevant entities. And that, of course, involves a bit of ingenuity to ask, what is it that I should now treat as quantum numbers? However, nature obviously doesn't do it like that. Nature is consistent throughout. It's quantum mechanical, universally, in my view, quantum mechanical at present. And classical physics just arises as a special case when you've destroyed all sorts of ability to superpose things in different directions, and you're only left with one direction in which you quantify information. And so I present you here with a picture as a quantum computer scientist would understand this as a sequence of bits, quantum bits, and each of them, the first qubit entangles to the second qubit, then the second to the third to the fourth. This is a bit like your Wigner's friend. The first qubit informs the second qubit and vice versa, then the second, the third, and so on. And they join in a big, if you like, depending on the number of qubits, entangled state. But in fact, if you look at any subsystem of these qubits, they're completely classical. They're only correlated in a classical way, up, up, and down, down, but as a mixture of the two, not as a coherent superposition. So quantumness exists only at the highest level for these kind of states and doesn't exist at the sub-level. And the thing on the right is basically a topological structure that reflects this property. These are the Borromean rings. And they're put together in a way that you can't separate them when they're like this together. But if you remove one of them, then all of the other ones simply fall apart. They are no longer entangled, if you like, in the topological sense of the word. So that's actually, in a way, how quantum information explains the appearance of classical information. And of course, classical information is simply just an exponentially small domain of the whole quantum universe. So why am I saying all of this? I'm saying all of this, and this is really the last point I want to make. I'm saying all of this because I think that following this logic, we're going to go far deeper. And one example here, there are many examples that I can think about, is this notion that we can actually come up with an experiment. And here I'm describing the experiment that Chiara Marletto and myself, and independently Sugato Bose and his colleagues came up a few years ago, is an experiment to use the logic of quantum information to test whether gravity is really quantum mechanical. At least some degrees of gravity are quantum mechanical. And I think this kind of experiment surprised many people because they didn't think that you could do a low energy experiment to test this. And the idea, just very briefly, is to take two massive particles in a superposition. Each of them is prepared in a superposition. But what then couples them together is the gravitational field. So you want to make sure that you eliminate any other form of coupling if possible, or you can control it. And you're really leaving it to gravity to entangle these two particles. And the question is, can that happen? And I think the reason why I'm putting this proving general relativity is because I think that this experiment will be done within the next 5 to 10 years. And I think, I'm betting, it will give us the first evidence that gravity ought to be quantum, at least at this level. And that's why I'm saying this proving classical general relativity. It will be the first bit of evidence that Q numbers are needed also in general relativity. And I firmly believe that that's the only consistent way to go. I have another, and probably won't surprise you, that I have another reviews of modern physics coming out anytime now, I think, on exactly this topic, the methods of quantum information in basically experimenting with gravity in the lab. So why is this, the punchline, why is this about quantum information? The reason is that you can think of, at the highest level, you can think of each of these masses as qubits in a way. You can think of the masses by being entangled are really communicating quantum information between each other. And then it becomes clear that if the channel that mediates this, and in this case, this is gravity, but the argument is very general, if the channel that mediates this can only handle classical information and not quantum information, then you shouldn't be able to create entanglement. That's why, by the way, no semi-classical description of anything works, in my view. Anytime we postulate anything semi-classical, like classical detectors, classical observers, any of these versions, they are wrong, basically, and they will be proven wrong experimentally as well. And gravity is just maybe the most exciting of these things to prove wrong. So in terms of information, if you could communicate a theory that has a larger capacity, if you could communicate by using a lower capacity theory as a mediator, you would violate all sorts of information theoretic principles. Things like the data processing inequality, for instance. It goes under various names. But the fact that you cannot increase the capacity as you copy the information further and further. If you could do this with classical gravity, you would violate effectively data processing inequality. So it's clear that information theory gives us a great insight into what we should be testing, how we should be testing it. And like I said, what I'm presenting here is possibly just the most glamorous example, but there are many others. The final slide. And it's just for fun. Rodolfo mentioned my book, Decoding Reality. And I use this because when you talk about this emergence of classical information, definitive information, out of these huge quantum states that only contain quantum information, they only contain Q numbers, they never really contain C numbers. C numbers are just relational, so to speak, in Everett's language. They're just relative. Somehow relative to one another, this information emerges. I always found it helpful, and it's a fun thing, to go back to something that John Wheeler used. So the question is, how does classical information come out of no pre-existing classical information? He loved these kind of things, dynamics without dynamics, charge without charge, and all of these things. That's all kind of Wheelerisms. So I always think about this game of card that's called differently in different cultures and languages. I think in England it's called Go Fish. So basically you have a bunch of players, and each of them starts with whatever cards. You deal cards around, and the whole point of the game, and I will tell you the rules, is to end up with the 4 cards of the same type, like 4 aces. And at which point you declare that you have 4 aces and you are the winner of the game. So there are 2 rules only. The game proceeds in a way that the first player can ask any other player if they have a card of a certain type, but they can only ask that if they themselves have one of these cards at least. So this is a beautiful illustration of how when we engage in a measurement, it's a perfectly symmetric thing. It's not that the measurement reveals information about the measured system, but it also reveals the information about the measurer. It's perfectly symmetric. Mutual information quantifies this exactly. That's why I think Shannon nailed it. It's got to be a symmetric quantity. So basically, you can ask for a card only if you have it. And of course, there is the rule number 2 is that you have to be honest. If you asked for a card and if the other player has it, they have to give it up to you. And that's how you end up collecting 4 cards of the same type. So basically, if the other player doesn't have that card, then you lose your turn, you go to the next person, and so on. And the game continues until one person collects the card. And now the amazing thing, and I always found this amazing, and I actually play this sometimes with my friends when we go to conferences, is that you don't need any cards at all to conclude the game. That's the punchline. In a sense that you can sit there and you can simply imagine having 4 or any number of cards of any kind. You could imagine cards that contain a snake, a cloud, a bridge, whatever else you like. You can have infinite domain of information, starting with just a bit mirroring the quantum numbers, if you like. Of course, not exactly quantum, they're still classical, but you allow any information possible. And it's interesting because of this consistency condition that you can only ask for a card if you yourself have that card. As soon as you ask for a card, it means you are revealing that you have at least one of those bits of information. And that's what allows you, and I encourage you to play it if you've never played. You can play it without cards. It's going to look awfully funny to people around you in a pub, I think, but actually it's a fun game. So somehow information really emerges out of the pre-existing soup, so to speak, which contains all possible informations. You can't just say it's one type of information. So I think this is going to help us with various breakthroughs, and I really do expect that to happen in physics in the near future. Thank you very much for your attention. Thank you. Pleasure.
Well, the next talk is going to be given by David Mazziotti from the Department of Chemistry and the James Franck Institute of the University of Chicago. He's going to talk about quantum simulations of many body systems. Please, David, could you share your research with us?
Okay, good morning, everyone. All right, it's great to be here. So again, thank you to Rodolfo and all of the organizers for the opportunity to address the symposium today. And so basically, following the line of Vlatko's talk on quantum information, this morning we're going to talk a bit about quantum information in the context of using that information for quantum computing, particularly for addressing the many electron problem in quantum physics and chemistry. So today's talk, I'm going to tell you a bit about exact Ansatzes for quantum simulations of many body systems. So first of all, just to kind of a little bit of background as we talk about quantum computing. So of course, we know that the problem basically of dealing with strongly correlated quantum systems is that as the number of strongly correlated electrons increases, essentially the computational cost of generating the many electron wave function grows exponentially, as we see here on the right-hand side, just from a typical exponential growth, with the number of electrons. And one possible solution is to rely on quantum information in the context of quantum computers to facilitate treating this exponential growth of information. Now, current quantum devices are in this noisy intermediate scale regime, which we call the NISQ era for quantum computing. And basically, in this particular regime, things like quantum phase estimation are basically not practical algorithms. And we've turned to things like, for example, variational calculations, i.e. the variational quantum eigensolver, as a potentially practical ansatz. And in the course of this talk, what we're going to do is we're going to take a look at some improvements that we can make to a variational type ansatz from the perspective of kind of quantum information, and more particularly, reduced density matrix theory. And we'll see in just a little bit why reduced density matrix theory is very important for thinking about quantum computing. So some of the limitations that exist in the variational quantum eigensolver algorithm, one limitation is that it doesn't really define an ansatz. And so you can basically choose any ansatz you like, but you still have to come up with a good ansatz to make the VQE algorithm work well. Some of the ansatzes have exponential scaling, and so they're really classically motivated ansatzes that don't really have the properties that would exploit the quantum information in an ideal sense. And also, the optimization of parameters within the VQE can also be exponentially expensive, which can cause trouble. And so questions are, can one formulate things in a way that essentially removes some of these limitations in working on the quantum device? And over here on the right, we actually just have a picture of one of the IBM quantum computers, and we can just see how delicate and complicated the hardware is to achieve the type of fidelity to perform quantum computations. So indeed, we are really exploiting quantum entanglement in a very full way. So to kind of transition and talk a bit about reduced density matrix theory and the parts that we're going to use in this talk, I want to talk about a family of kind of alternative algorithms to the variational quantum eigensolvers. So rather than VQE, we're going to talk about something called contracted quantum eigensolvers, or CQE. And the idea of a contracted quantum eigensolver in the quantum computing sense basically traces back to work on the contracted Schrodinger equation. And so the contracted Schrodinger equation, just kind of to go through this, we start with the Schrodinger equation itself. So just our typical Schrodinger equation as the first line. And then what we're going to do is we're going to contract it onto the space of 2 electrons to get a 2-electron contracted Schrodinger equation. And to do that, we define a set of 2-body test functions. So here we can see we have a ket psi, a dagger, AA, where the indices I, J, K, L represent orbitals. Okay, so it could be any set of spin orbitals, fermionic orbitals. And then we contract, and that contraction process is sort of synonymous with a projection onto this space of test functions. And we have here our contracted Schrodinger equation. Now, what's very exciting about this equation, first proven by Hiroshi Nakasuji in 1976, is that this equation basically implies the Schrodinger equation. So if we take a wave function that satisfies our 2 contracted Schrodinger equation, then that wave function will also satisfy the Schrodinger equation. Okay, so it's not just that satisfying the Schrodinger implies the contracted Schrodinger equation, but remarkably the opposite is true, that satisfying this contracted equation satisfies the Schrodinger equation itself. And the proof basically corresponds to showing that the contracted Schrodinger equation implies the variance, and then the variance implies the vanishing of the variance implies the solution of the Schrodinger equation. Okay, so this is our contracted Schrodinger equation. Now we can take the contracted Schrodinger equation and divide it into two parts. And so we first write down our CSE, and then in the next line, we divide it up into a Hermitian component and an anti-Hermitian component. And the anti-Hermitian component will designate as the anti-Hermitian CSE, or ACSE. And we can see that's the expectation value of now the commutator of a set of essentially two-body operators and the Hamiltonian operator, looking when that is 0. And we'll see that the ACSE, both the CSE is very important for quantum computing, but the ACSE also has a very nice interpretation in terms of unitary transformations, which are very easy to perform on quantum devices. Now, first, before we talk about the quantum algorithm, let us first talk about the classical algorithm that was developed for solving both the contracted Schrodinger equation and its anti-Hermitian part, the ACSE. And so ultimately, the ACSE depends not just on the 2-electron reduced density matrix, but also on the 3-electron reduced density matrix. So to really remove its indeterminacy, we need to reconstruct the 3-RDM from the 2-RDM. Okay, and we did this in original work, basically where we basically built the 3-RDM by its cumulant expansion as an approximation from the 2-RDM. So here you can see, introducing the Grassmann wedge product, we have a series of wedge products of the 1-RDMs. The delta 2 represents the cumulant part of the 2-RDM, the 2-RDM minus the wedge product of the 1-RDM with itself. And finally, we have the cumulant part of the 3-RDM, the delta 3. And so if we, for example, approximate delta 3, we can either approximate it in some way or, for example, assume that it vanishes. And that gives us an approximation for the 3-RDM. And then with that, we can go ahead and solve the contracted Schrodinger equation or the ACSE. Okay, so this work on the reconstruction was done kind of back in the late 1990s in some of the work cited here. But now, in terms of solving the ACSE, ACSE has kind of emerged as a very powerful method for treating correlation and strong correlation. And here you can see its performance on a benchmark, comparing it to a series of other methods in electronic structure theory. So both, for example, quantum Monte Carlo methods like auxiliary field quantum Monte Carlo, as well as, for example, complete active space theories using multi-component pair density functional theory, as well as a variety of different techniques. And you can see that in terms of mean signed error and mean average error, that the ACSE essentially is performing better than these other methods, or at least as well as some of these other state-of-the-art methods which are used in electronic structure theory. So again, all of this is being done, in this case, to calculate a series of singlet triplet gaps in a benchmark system. But the important take-home message is just that even with the classical approximations of solving the classical equation, reconstructing approximately the 3-RDM from the 2-RDM, we can come up with very accurate solutions to the ACSE. Now, one more example before we move on with the classical calculation. Here's an example where we can look at the photoexcitation of gauche butadiene. And it's quite interesting because the photoexcitation kind of rearranges on an excited surface through a conical intersection where it hops down to the ground surface in a geometry very similar to the disrotatory transition state. And then that rearranges back into a cyclic structure, the bicyclobutane. And the conical intersection was actually not known, but was postulated to be near the disrotatory transition state. And we were able to use the ACSE to track down this conical intersection, in part because the ACSE, by essentially giving an initial guess from a CAS-SCF calculation, and then using the ACSE to build correlation onto the CAS-SCF, we were able to generate the states that were degenerate between the ground and excited states at the geometry of the conical intersection. Importantly, more traditional methods like coupled cluster give you a very large energetic gap between the ground and excited states at the geometry of the conical intersection due to basically the inability of the excitations in a, for example, truncated coupled cluster singles and doubles to capture the strong correlation that's necessary to produce the conical intersection. So again, another example where quantum information and entanglement are critical to really generating the physical reality, in this case, of these portals, these conical intersections connecting the excited states back down to the ground state. And of course, very important in treating non-adiabatic dynamics. So now we kind of transition into talking more about the idea of contracted quantum eigensolvers. So the contracted quantum eigensolver, or CQE algorithm, basically goes ahead and tries to solve the contracted Schrodinger equation or the ACSE directly without essentially regard to the Schrodinger equation. And this has a big advantage because now we're essentially just minimizing the residual of the ACSE. And because it's projected on the space of 2 electrons, we can perform just 2-body measurements, which essentially are not going to grow exponentially on the quantum computer because we have 2-body measurements regardless of essentially how large our quantum system is. So here, as now more details. So basically, we can look at the residual of the ACSE, and we can define that as a tensor matrix. In this particular case, we represent it as an A for the antisymmetric part of the CSE. In terms of the indices I, J, K, L, we introduce an index N, where N represents an iteration. And so we can think of starting off with a trial wave function where we do not solve the ACSE, and then we're going to iteratively improve our trial wave function to make the residual of the ACSE, or CSE, as we'll talk a little bit later, to go to 0. And we introduce an iterative wave function Ansatz, and you can see that here where our n+1th wave function comes from essentially the exponentiation of epsilon times this antisymmetric matrix, the residual of the ACSE, times the wave function. And it turns out then the residual of the ACSE defines then through this exponentiation a unitary transformation that moves our wave function from the nth iteration to the n+1 iteration. And so this gives us a way of generating kind of a well-described ansatz for moving our quantum many-electron system from, for example, an uncorrelated state, like a many-electron Hartree-Fock state, to essentially a correlated many-electron quantum state. And so how would this actually work? Well, essentially what we're doing is the following. We're going ahead and we're taking a step forward we're preparing essentially a wave function through a certain number of these iterations. And then we're going to measure the 2-RDM. Okay, so the 2-RDM then gives us the sort of the result at a particular iteration, let's say n+1. But then what we do is we take that wave function on the quantum device and we hit it with a unitary transformation in terms of e to the I delta h. And what that allows us to do in our second line is to extract a quantity which we can see here we represent as lambda. Okay, so we have lambda 2 plus or minus IJKL, our capital lambda. And capital lambda is a really important thing to measure on the quantum computer because by taking a finite difference of the lambdas, we recover the residual of the ACSE. Okay, so the ACSE's residual can be measured on the quantum computer, okay, simply by looking at a unitary transformation that propagates us in the Hamiltonian and then using finite differences to extract that residual. Now what we're going to do basically is take that residual and then form our contracted quantum eigensolver in the following way. We start off on our left-hand side, upper left, by initializing our 2-RDM, okay, a 2-electron reduced density matrix. And then what we're going to do is obtain the residual of the CSE, of the ACSE. And then what we're going to do is take that residual from those measurements of the lambdas. And if it's not small enough, we'll go ahead and use that residual to update the wave function and construct a new wave function, psi n+1, okay, which essentially has this exponential, this unitary transformation applied to psi n. And then we'll check the energy there, and we're going to basically update our epsilon, minimize over the parameter epsilon, a learning parameter, to basically come to a minimum energy. And then we'll go ahead and measure the 2-RDM again, and then we'll construct the residual. And we'll just repeat this process cyclically as we iteratively construct a wave function. And we can see we're iteratively constructing an ansatz, which is an ACSE ansatz, because the ansatz that's inspired by essentially using the solution of the ACSE within a contracted quantum eigensolver algorithm. Now, we can actually use the residual directly, but we can also essentially use, for example, other optimization techniques than a gradient. For example, we could use a quasi-Newton method, and we've done this where we use a BFTS algorithm to basically come up with a little bit more accurate search directions. And we can use these addressed search directions to minimize the energy as well. Okay, so that basically there's kind of a lot of flexibility in the algorithm that we can use. So let's talk now a little bit about some of the early applications. There's some examples and then some applications of using the contracted quantum eigensolver on a quantum device. So just a very toy problem, we can actually just take the block sphere. And if we have the block sphere, we could start off, for example, up in the top there at the plus Z component. And then what we're going to do is we're going to do a series of ACSE iterations. And what we see is the green dots kind of tracking along the surface of the block sphere, taking us to the tip of the blue arrow. So the tip of the blue arrow is the solution, okay, of the particular problem that we've coded here in terms of 1 qubits. And you can see in about 9 iterations, okay, 9 green dots arcing around the circle, we reach the tip of the blue, the solution, okay, of our problem on the block sphere. Okay, so it gives an idea of what the ACSE is doing. Is it's performing a rotation, in this case, in essentially the world of 1 qubit. But when we're dealing with a many-body problem, we're performing a more complex rotation in a many-body space. So kind of moving along from 1 qubit, we can look at solving the hydrogen molecule on a quantum computer, which is sort of the simplest of things to do on a quantum device for chemistry. And what we have here is the full CI for this problem is the black line at the bottom. And basically the red curve represents just a solution where we're just doing it, solving the ACSE, but just with stochastic sampling. And you can see that we can converge in about 15 iterations to our result, our full CI result. However, then we can basically solve our quantum ACSE on the quantum computer. And this is on an actual quantum device from IBM. And what we see is the blue curve then, iterates along. And again, in only about, 10 iterations, we pretty much reach our steady state where we have our solution. But now what's important to note is we haven't reached the exact solution, but that's not due to a limitation of our contracted quantum eigensolver. The CQE algorithm is effectively exact. So if we don't have noise on the device, we'll recover the exact solution. However, you can see from the blue curve, we're essentially up by about 30 millihartz too high. And again, that's due to the fact that we have depolarizing noise on our quantum computer that's keeping us from reaching the full possibility, of the exact answer. However, what's really important is if we actually repeat this calculation throughout the bond breaking of H2, we know at equilibrium, we basically have just what's called dynamic correlation, or essentially a perturbative regime around the Hartree-Fock reference. Whereas if we stretch our molecule out, we end up in the non-perturbative regime where the two spins become highly entangled. And regardless of whether we're in the entangled region or the perturbative region, the quantum computer pretty much gives us the same 30 millihartz upper bound on the curve. So the shape of the potential energy curve is actually very accurate throughout the process. And so that's a really important aspect of this, showing tremendous promise for simulating systems on a quantum system, because the quantum state, really, the noise is not the same as essentially having kind of a perturbative error in the system. Okay, so we can also look on a simulator just to see how accurately we can do this if we're just kind of using a certain amount of finite precision, and just to show the accuracy of the CQE in a classical execution of it without noise. And so here's the CQE for H3. And interestingly, you can kind of compare that to a classical solution of the ACSE in red. So classically, when we solve it, we need to make some approximation on the reconstruction of the 3RDM. And so we can see that the error, the log error, definitely performs better in the equilibrium region than it does in the entangled region as we stretch the molecule apart. However, okay, and this is again 3 hydrogens all being stretched out equally as we equidistant stretching of the H3. The quantum computer, you can see we get 10 to the minus 10 accuracy basically throughout the bond breaking. And again, 10 to the minus 10 is simply because we solve this with a precision on the classical device of 10 to the minus 10, but we can recover essentially an arbitrary precision from our calculations. Okay, so let's kind of move beyond H2 and H3 and look at a bigger molecular system to get a sense of whether we can capture some of the effects that are actually important in true multi-reference or strongly correlated, or at least statically correlated molecular systems. So one example, which is very important in quantum chemistry for benchmarking and also an important problem in and of itself, is looking at the isomers of the benzene molecule. So here we're looking at the ortho, meta, and para isomers, conformers of benzene. And what's important is that the ortho isomer is not very correlated. Meta is a little bit more correlated. And then the para is approaching a biradical. And you can see this in the highest occupied and lowest unoccupied fillings. Or here we have the natural orbital occupations are being shown here. So the eigenvalues of the 1-RDM, we can see the degree of correlation increasing as we go from left to right. And so what we'd like to be able to do is reproduce the proper energetic ordering of these isomers. You can see Hartree-Fock gets the ordering correct, however, with the para being highest, but the gaps between the different isomers is definitely incorrect. And the para is much higher than the meta and the ortho, because essentially Hartree-Fock cannot capture the strong correlation effects. So if we go to a classical 2-electron, 2-orbital calculation, CAS-SEF calculation, that significantly improves the situation by allowing us to have the biradical character of the para isomer captured, and we can see that the gap shrinks down to much, much smaller, and that's much more accurate. Interestingly, on a quantum device, we can do a 2-2 1-qubit version of this, and we can recapture with the CQE the spacing quite nicely. We can also go to a bigger active space of 4 electrons and 4-orbital CAS-SEF calculation. If we use a 3-qubit approximation to the 4-4 space now on a quantum computer, moving to the right on our legend there, we reproduce the gaps quite well by solving each of the species on the quantum computer. And we're using L+. The L+ basically means that we're using error mitigation techniques. In particular, we're using an error mitigation technique where we restore the unrepresentability of our measured 2-RDMs on the quantum device. And I'll talk more about that in just a moment. But if we try a 4-qubit calculation, you can see that the gaps are still not bad, but actually a little bit worse. So it's an example where actually creating a more sophisticated 4-qubit calculation on the quantum computer ends up producing a result that's worse, because the degree of noise created on the quantum device is actually greater. It's greater than the entanglement basically resource that we've increased due to increasing the number of qubits. So to show that we're actually not just calculating energy gaps, we can also look at the occupations being recovered from the 1-RDM, tomographied on the quantum device. And if we compare on the top, we have the occupation numbers of the highest occupied natural orbital -1, so the HONO, the LUNO, and then the LUNO +1. And we can see that we have basically 3 columns for ortho, meta, and para going from left to right. And we can see the para column definitely has much more occupied full CI occupations for the HONO LUNO than the ortho and the meta. And we can see our contracted quantum eigensolver, our solution of the ACSE, reproduces basically those fractional occupations of the para. And that's really important because it shows that we are capturing the entanglement, on the system in the 1-electron reduced density matrix, the entanglement that's allowing us to obtain good energy gaps in the system. So it turns out then that we can turn to 2-RDM methods and 2-RDM ideas. We're using the 2-RDM ideas in shaping and crafting our contracted quantum eigensolver, because the theory upon which it's built, the contracted Schrodinger equation, is really the fundamental equation in 2-electron reduced density matrix theory. But we can also use other aspects of 2-RDM algorithms to improve the quantum computer, in particular with respect to the issue of noise. So noise on a quantum computer, if we think of the quantum computer as potentially a super machine or a superman, then to some extent, noise is the kryptonite to the quantum computer, similar to kryptonite and Superman. And so what we can do to try to deal with this kryptonite and this noise is to use 2-RDM methods to mitigate the error. So when we measure a 2-RDM on the quantum computer, we can check if certain conditions for the 2RDM are satisfied. So we know that a 2-electron reduced density matrix, to be n-representable, to represent an n-electron quantum system, has to obey a certain set of constraints known as n-representability conditions. An important set of these conditions, an important necessary set of conditions, are the 2 positivity conditions. And they correspond to keeping 2 holes, 2 particles, and a particle hole positive semi-definite. And so we can actually see that here. So we have our D2 matrix, which is the particle-particle matrix, our Q2 matrix, which is the hole-hole matrix, and our G2 matrix, which is the particle-hole matrix. And we're going to keep each of these matrices positive semi-definite, which basically means that their eigenvalues are non-negative. And so we have a non-negative probability distribution with respect to both 2 particles and 2 holes in the fields of the remaining system. So to achieve this, what we can do, one approach, is to use semi-definite programming to find the 2RDM that satisfies these n-representability constraints that's as close as possible to the 2RDM measured on the quantum computer. And so we go ahead and we basically minimize the least squares distance between these matrices using a semi-definite program and putting on the constraint onto the elements of D2 that we want to capture that nearest 2RDM. And so we've done that in the work on the benzynes. We basically did that in the PRA discussed here in this 2022 paper. And those ideas of sort of introducing this purification, if you will, this correlated purification of the 2RDM, we had kind of previously looked at that from an experimental point of view in work with Foley from 2012, as well as earlier work on correlated purification from the early 2000s. So we can also then think about, well, it's interesting to have a complete active space calculation on the quantum device, but we also know in chemistry that we also care about all electron correlation. So one question is, how easy would it be to take a calculation on a quantum computer and then adjust it to deal with essentially the other correlation, for the other degrees of freedom? And it turns out using traditional wave function techniques, such a correction is not so easy. And the problem basically comes up from the following. You can run your CAS-SCF and you end up with a CAS-SCF wave function, but then you don't want to measure that entire wave function on the quantum computer. Otherwise, well, you can measure that wave function, but you basically still have you don't really want to measure it ultimately because you're going to basically have exponential scaling with regard to the size of the active space. So you could do it, but it would basically really limit the advantage of the quantum algorithm. So instead, what you can do is measure just the 2-electron reduced density matrix. But then there aren't necessarily algorithms in the wave function land to take the 2RDM as an input to then calculate the correlation of the remaining orbitals. And so that's where an advantage of reduced density matrix theory comes in, because RDM methods are really designed to take the 2RDM from the active space and then build the dynamic correlation on top of that. And so that's basically what we can use. The anti-Hermitian contracted Schrodinger equation theory was developed to add the dynamic correlation to an initial guess for the 2RDM. And that guess can come from Hartree-Fock or a complete active space SCF calculation. So basically here, what we do is we combine CQE to calculate an active space 2RDM, and then we basically correct that using ACSE or multi-configuration pair density functional theory. So this was joint work with Laura Gagliardi here at University of Chicago, and we tried these 2 different methods as a way of correcting it. So we basically on the bottom perform the usual CQE algorithm, but then we kind of come up into this green box at the top to do a classical dynamic correlation calculation correction. Okay, here are the results showing essentially the classical result on the left, and then comparing it with a 1-qubit calculation. And you can see the 1-qubit calculation for a 2-2 active space, essentially for the benzynes. Again, we're looking at the benzyne isomers. We recover now all of the correlation very, very accurately for all of the electrons and kind of match the classical calculation. And again, this is with reference to an accurate classical calculation of the situation using the ACSE. And then if we basically now go ahead and do a 4-4 active space calculation, we can see with 3-qubit and 4-qubit calculations on the quantum device, we also really match the dynamic correlation and the gaps between meta and ortho and para and ortho. So these are the energy differences between the meta isomer and the para isomer relative to the ortho isomer. We can see the quantum calculations match the classical calculations after we've added in the dynamic correlation from this post-processing of our quantum result. So we can kind of take a step back now and try to put some context of how does contracted quantum eigensolver relate to other methods. So for example, you can kind of look at how the CQE has overlaps with, for example, the coupled cluster ansatz, as well as hardware efficient variational quantum eigensolvers. The difference basically is that the CQE is not performing a full variational calculation. So it's not a variational quantum eigensolver in the traditional sense. Instead, we're performing a VQE calculation essentially just at each iteration. Okay, and then essentially the parameters are not being re-optimized after that. And the advantage of that is that it really gives us a very efficient ansatz for the wave function that also is exact. So it's sort of in the exact quadrant, but it has basically overlaps with being also very efficient and fast, like hardware efficient type approaches or coupled cluster ansatzes. But again, the coupled cluster, if we truncate it at a given level, will be approximate. Whereas here, with our contracted quantum eigensolver, we're able to essentially capture strong correlation effects. So VQE, basically, one important aspect of it is it doesn't really define the ansatz. So for example, if we pick a unitary coupled cluster single double ansatz, then essentially that becomes our ansatz that we're using relative to full CI. Whereas in contracted quantum eigensolver, we have a built-in intrinsic ansatz that essentially is exact, where we basically then can converge the situation, converge our wave function to the full CI, capturing the strong correlation. And I really firmly believe that it's very important in developing quantum algorithms, both in the noisy intermediate scale regime, as well as in future fault-tolerant regimes, to have algorithms that can really capture the strong correlation. Because that really, capturing the entanglement is really where the advantage of the quantum computer is going to come in. Because we already can do classical calculations that very accurately generate coupled cluster-like ansatzes. Now we can also compare to the adapt VQE. There are connections too, because in the adapt VQE, it was in many ways inspired by literature in the contracted Schrodinger equation area, where you would iteratively update the wave function. And so adapt VQE actually uses an ACSE ansatz, but it differs in an important way from contracted quantum eigensolver. The most important difference is that adapt VQE aspires to be a variational quantum eigensolver. So at each iteration, all parameters at all iterations have to be completely re-optimized. Otherwise, we're not at a variational minimum. And so the adapt VQE has a much higher cost than what we have in our contracted quantum eigensolver. So we can also treat excited states. And so in the remaining minutes of the talk here, I just want to cover a couple of areas and extensions that we can do. So for example, we've extended this to excited states by minimizing not the energy, but rather the variance itself. And so you can see here, we can minimize the variance subject to still using our CSE, ACSE ansatz. And sort of the algorithmic details, again, very similar to what we had for the ground state. So we can kind of skip over these particular details. But here we have some examples performed on essentially a classical simulator of the BH molecule. And you can see we can very accurately, for the first basically 3 excited states, capture the potential energy surface of breaking the BH bond with our CQE solver for excited states. Okay, likewise, we can take the H4 molecule and we can basically look at its first 15 excited states, and we can calculate the energy, within 10 to the minus 7, the variance within 10 to the minus 7, and basically the CSE norm within 10 to the minus 8 by basically not too many iterations. So basically a handful of CQE iterations of the ACSE in this case for our variance-based method, somewhere between 20 and 40 iterations per excited state. And again, each state is being calculated separately. Okay, so we calculate each state separately from our CQE. So it's a single state excited state method. We can also do conical intersections. And so conical intersections, as we mentioned earlier, are important places where 2 potential energy surfaces essentially meet in a cone-shaped topography and are very important for a number of many different situations for energy transfer. They show up, for example, in the glow of the firefly at night. They show up in rhodopsin, being important for vision. So here's an example of basically the reaction in rhodopsin that, again, it has to do with geometric changes in the molecule that cause potential energy surfaces to come together at a conical intersection. And these are points where you can have basically radiationless energy transfer from the ground to from the excited state back to the ground state. Here in this paper, just to kind of get a sense of computing a conical intersection on a quantum device, we basically took H3 plus and we mapped out the ground and excited states. And this is on a quantum device. And so you can see, even with the noise on a quantum computer, we were able to capture kind of the gap itself definitely gets very narrow in the region of the conical intersection. We can do a little bit more exciting molecules by looking at conical intersections in things like cytosine, okay, DNA base pair. And here you can see for this conical intersection, well, on the left, we actually have a variational quantum deflation. On the right, we're showing the CQE algorithm. And we'll focus mostly on the CQE. And you can see in a handful of iterations, we basically end up getting our ground and excited states to converge to the same energy. And so we have the conical intersection. We need more iterations on the left with the quantum deflation, but we tried to gauge the calculations to have a similar circuit depth. However, the quantum deflation is being treated kind of in a physics agnostic approach, whereas with the contracted quantum eigensolver, we're building the physics of the Hamiltonian into it. So we can essentially do much larger systems than this particular cytosine using a CQE approach. Likewise, here now, we basically look at what happens again, but now this is actually on the quantum device. The other one was a simulator. Here we have the quantum device. And you can see even with the noise on a quantum device, we're still able to capture the degeneracy of the conical intersection. Okay, and here's a picture of what the conical intersection would look like based on a quantum simulator, basically without noise on the left. And then essentially here's the calculation on the quantum computer. And you can see again, we're still able to geometrically reproduce it's not perfectly degenerate, but it's quite degenerate considering the degree of noise on the IBM machine that we're using to simulate the conical intersection. Okay, so I have two quick stories to tell in the last few minutes of the talk here. The first basically is the idea of a CSE-based contracted quantum eigensolver. So a lot of our calculations have used the anti-Hermitian part of the contracted Schrodinger equation, but we also can solve the contracted Schrodinger equation directly, its residual, on the quantum device. The main difference is the residual, the CSE, produces a transformation that's not unitary. So it turns out, of course, the Ansatzes is quite nice. Again, we know that the solution of the CSE will imply the Schrodinger equation. And so the CSE is satisfied. So the advantage of the CSE is it's kind of a verifiably exact solution. And if we check the CSE and we see the residual has vanished, we know that the Schrodinger equation is satisfied by our wave function. Okay, but we have to deal, basically, the challenge is that we have to deal with non-unitary transformations of the wave function. So we can get around that, though, by essentially doing the following. We can represent our wave function as basically a series of unitary, okay, and non-unitary transformations, okay, that we can apply. We can interweave these transformations. And for the non-unitary transformations, we can perform them by using a 1-qubit dilation to dilate our non-unitary transformation back into a unitary transformation. Okay, so we do that here, and you can see the dilation. This is the dilation process is kind of shown here. And then we perform a measurement to calculate the residual of the CSE. And then we continue propagating the wave function through the dilation. The circuit kind of looks like this. And here's some examples of it. So for example, if we're solving H4, and in particular, what we're looking at here is H4 passing through the square to rectangular transition. And there's going to be a cusp at the rectangular geometry for H4 in Hartree-Fock or coupled cluster theory. But you can see the full CI doesn't have this cusp because it moves between the references in a very smooth way. And so do the ACSE and CSE solutions on basically our contracted quantum eigensolver with the CSE on our quantum device. And you can see that if we do this without noise, we can lower the error in the residual on the contracted Schrodinger equation can be decreased down to 10 to the minus 13 as basically a linear line with the variance. So as the variance is getting small, meaning the Schrodinger equation is being satisfied, we're satisfying our contracted Schrodinger equation too. So essentially forcing the residual of the CSE to vanish is also giving us a solution to the Schrodinger equation. Okay, so the final thing I would like to talk a little bit about is using the CQE more generally for example, creating a fermion boson ansatz to deal with mixed particle statistics. So we're not limited to just fermions. We can also treat many body systems of bosons or even joint systems of fermions and bosons. So here we have a fermion boson, a generic fermion boson Hamiltonian, where we're essentially using some vector indices to represent products or strings of creation and annihilation operators. The I, for example, and the K represent strings of creation annihilation operators of fermions, whereas the J and L represent strings of annihilation creation operators for bosons. And so by writing a generic fermion boson Hamiltonian in this fashion, we can kind of in a very simple notation, write down the contracted Schrodinger equation for mixed particles. So we basically contract it onto the same space here of this gamma hat IJKL, and now we have our contracted Schrodinger equation. And this basically then suggests an exact ansatz for mixed particle systems, where we essentially have this exponential of a unitary transformation of a two-body anti-Hermitian matrix, followed by the exponential of a two-body Hermitian matrix. And this gives us a way of essentially propagating our wave function through just two-body transformations for mixed particle systems. We apply this at first just to a Tabas-Cummings model, which is basically n levels that are now basically interacting with a boson bath. And you can see that while basically QED calculations based on coupled cluster theory really fail as we increase the interaction strength, we basically, with the CSE ansatz, we match essentially the exact results throughout, increasing the coupling strength and the energy. And likewise, in terms of the occupation number of the diagonal elements of the 1-RDM, here the occupation of the ith position of the lattice, we're basically capturing the stair-like behavior that comes in the exact solution as a function of coupling strength. Whereas you can see coupled cluster theory is producing a smooth behavior that misses the sort of the sharpness of these transitions. Okay, so with the final minute here, I want to just show here's a result showing the results on a quantum device, showing that even in the presence of noise, we're able to capture these effects. Finally, we can look at polariton chemistry as well. This is the Pauli-Fierce Hamiltonian. And as a function of essentially the coupling of basically our electronic degrees of freedom with our light in a polaritonic setting, we can actually see, again, this is for the H4 transition from square to rectangular. We can see that even in the coupling to light regime, we're able to capture the transition with essentially a very smooth transition. Whereas you can see the gradient that would come up from coupled cluster is going to be discontinuous, whereas ours is very smooth. Okay, and similarly for the occupation numbers, a similar thing is found. Okay, so pretty much just wrapping it up. So the contracted quantum eigensolver provides an efficient way for basically solving problems in many electron theory on quantum devices. And it has basically a lot of advantages because kind of in its heart, it really uses reduced density matrix theory to essentially produce a very efficient way of dealing with quantum information on the quantum computer. So I just want to finish up here by acknowledging my research group, 2 different group photos from 2 different periods, but a shout out to everybody who contributed, especially Scott Smart, now a postdoc at UCLA with Pri Narang, as well as my current postdoc, Yuchen Wang. And shout out to basically everybody in the group for all of the help. And I want to just thank everybody for your attention today. Thank you so much. It's great to be here.
Well, thanks, David. We appreciate your participation. Again, for the general audience, I would like to remind you that we don't have any Q&A session, synchronically, I mean. So you can forward any questions to David through the link we have in WhatsApp. Thanks again, David. Well, we can go ahead with the next guest. It's Christian Schilling. from the Arnold Sommerfeld Center for Theoretical Physics in Munich, Germany. He's going to talk about basically electron correlation. Christian, please go ahead.
Hello, everyone. Can you hear me?
Yes, we can hear
you. Can you hear me?
Yeah.
Okay. Can you also see my mouse cursor on the slides?
Yeah.
Okay. Yeah. So hello, everyone. First of all, congratulations to the 50th anniversary of your institute, and thank you very much, actually, for the invitation. So I would like to use this as an opportunity to provide an overview presentation covering some of the main activities of my research group in Munich. And it's also wonderful to be part of this session with Vlatko and David, because as you're going to see, my research actually aligns very nicely with the previous two talks. So one of the main research themes in my group is this electron collation problem. So from a very general perspective, we are looking at many identical particles, typically electrons, subject to some confinement potential. And then one of the first scientific questions you can ask is, what are the properties of such a system at 0 or low temperature? So in the first step to address this, you would actually need to determine the ground state energy of such a system and the ground state. And we all learned how to do it, at least in principle. So you take the Hamiltonian of your system, and you would minimize it over all this expectation value over all n-fermion quantum states in your Hilbert space. But this is exactly where the problem comes in, namely the Hilbert space grows quite a bit as you increase the system size. So from a very general point of view, without referring to potential structural simplifications of Hamiltonians, you would conclude that this problem is hopeless in practice. But as I already mentioned, and as we all know, realistic Hamiltonians exhibit a lot of simplifying structures. So I have here two striking structures in mind. The first one is referring to the particle picture based on first quantization. So independent of how many particles we have, the electrons interact typically only by pairwise forces. So you see only electron I and J coupled to each other via such a pair potential. And exactly this pair potential decays also in spatial space. So when you go to second quantization, you directly understand that 2 points in space couple weaker and weaker the further you separate them. So this is true for the Coulomb interaction, and it's even more true for the Hubbard on-site interaction and for fundamental forces. So in that way, you could kind of summarize our research ambition, which is about not only exploring and quantifying the structural consequences of those two aspects, but also to exploit them to their full potential and on the same footing in order to find a more systematic approach to the electron collation problem. So therefore, the talk will be consisting of two parts. The first part, I'll focus on the particle picture, and the second one on orbital or mode or site picture. And in each of those two parts, I'm first going to recall some hopefully well-known ideas of how scientists in quantum chemistry and quantum many-body try to exploit the consequences of those two structures. Then we change to quantum information, and we're going to discuss whether a notion of correlation or entanglement actually exists between particles or between orbitals. And then potentially in the most exciting part of this presentation, we are merging these two worlds or perspectives, quantum information and quantum many-body. And then I'm going to present a couple of our results, and hopefully I could convince you that this interface of quantum information and quantum many-body is potentially very, very exciting and very promising. And always please keep in mind, the ultimate goal is to find a more effective approach to the electron collation problem. So let's actually focus on the particle picture. Okay, first quantization. So we're asking, what are the electrons doing? So first of all, I would like to share also in particular my research vision, and also I think it aligns very nicely with David's general research vision. So to obtain the ground state, we would need to minimize the energy expectation value over all n particle quantum states. So here I relaxed the purity constraint and even allow or even consider all ensemble states. And this has actually the advantage from a conceptual point of view that the underlying search space becomes convex. So from a practical point of view, it's maybe not a good idea, but it allows me to illustrate some aspects in a very nice way. And one aspect that it definitely illustrates is that here we are concerned with the minimization of a linear functional on a convex space. So you obtain then always the minimum on the boundary. But now by looking at this expectation value, we can directly see that the first structural simplification can be exploited in a very direct manner. So we can integrate out all fermions except 2 and address exactly the same problem through the much simpler 2-particle reduced density matrix rho 2. Of course, there's a caveat now, namely a significant part of the complexity of the original problem is now transferred into the problem of describing the set of exactly those 2-particle reduced density matrices rho 2, which are corresponding to an n-particle quantum state. This is actually a really hard task. Okay. But now, if you think a little bit more about this, you can ask yourself, if you had now such a solution to this problem, actually it would allow you to solve the ground state problem for every pair interacting Hamiltonian. But who is actually interested in solving the ground state problem for every pair interacting Hamiltonian? In quantum chemistry, for instance, we care only about Coulomb interaction. In condensed matter, it's about Hubbard on-site interaction. In the field of ultra-cold atoms, maybe the contact or delta function interaction. So you see, if you're very, very ambitious in your whole lifetime or as a scientist, you would like to solve the ground state problem for many Hamiltonians. All of them could have different particle numbers. They could be all characterized by different external potentials, maybe even by different hopping rates as they can be varied in ultra-cold atom experiments, but you definitely do not want to change the pair interaction. So the pair interaction W is fixed. And if you ask from a conceptual point of view, what would be actually the right variable to refer or take into account the scope of such a lifetime task? It's actually the conjugate variable to the 1-particle Hamiltonian. And the conjugate variable is actually the 1-particle density matrix rho 1. Because the rho 1 is exactly the simplest or smallest quantity you need to know in order to be able to calculate the expectation value for every choice of the 1-particle Hamiltonian H1 via this standard formula that we all learned in quantum mechanics a long time ago. And now it's given this general motivation of this perspective, I think it's not so difficult for you to believe that there exists a so-called universal functional FW, which takes care of the pair interaction effects of rho 1, and it's actually universal in the sense that it does not depend on the choice of H1. This has actually remarkable consequences because it allows all the scientists in a scientific field characterized by the fixed W to approximate the same common universal functional, so that it can dedicate, thousands of people can dedicate a lot of time and effort to approximate the same functional FW, and then afterwards, after let's say 10 years, everyone can use this approximated functional to solve ground state problems for the remaining decades in their lives. So you see, functional theory is not just an alternative approach to wave function-based methods, but on the long term, they're particularly economical. And from this slide here, I would say there are 2 take-home messages for you. First is exactly my research vision why functional theories are so wonderful. But the second take-home message, also relevant for this presentation, is that this reasoning identifies the 1-particle reduced density matrix as a particularly exciting quantity. So now let's completely forget about physics and chemistry, and let's talk about entanglement and correlation. So I'm wondering, can we talk about entanglement between identical electrons? So for this, let's briefly recall the formalism in quantum information theory that Vlatko already addressed. So I keep it very short. So for simplicity, I'm studying bipartite systems, Alice versus Bob, A versus B. The Hilbert space of the joint system is given by a tensor product of the 2 Hilbert spaces of Alice and Bob. And the same holds true for the algebra of observables for the joint system. Okay, so here I always assume finite dimensional systems, Hilbert spaces, so to avoid some mathematical subtleties. And now by having introduced this basic notation, we can actually make it very precise what we mean by a quantum state being uncorrelated. So let's say I give you a state rho for Alice and Bob, the bipartite state, and we refer to the state as being uncorrelated if and only if the expectation value for any product of local measurements, A hat on Alice's side, B hat on Bob's side, factorizes. Okay, so in many cases, in particular for distinguishable particles, this typically means that the quantum state itself can be written as a tensor product of a state for Alice times 1 for Bob. But when you apply this to fermions, it's kind of a little bit more subtle at the end. And then it turns out that this first more general definition is more robust, and this one becomes a little bit obsolete. So because in practice, actually will turn out that the algebras of observables for fermions are like not including all the Hermitian operators on your respective Hilbert spaces. This is a little bit the point behind it. But for the moment, just assume a state is a product state if it takes this form here, or it's called uncorrelated. So now let's imagine as an experimentalist, you're taking a coin and we are flipping the coin, and depending on the outcome, we are preparing either the system in one product state or in a different product state. Well, in that case, clearly, we're going to have some collation in our quantum state, right? But definitely no entanglement. And this is, to some degree, like a motivation for the notion of unentangled or separable states. So a density matrix or a quantum state is called unentangled if it can be written as a classical mixture of product states. So this is already what Vlatko told you in his talk. And what I like a lot about these different sets is you can illustrate them in a cartoon by referring to the geometry of quantum states, also what David referred to some degree with his two RDMs. So here, in the case of Alice versus Bob, you see in light blue the convex set of all bipartite density matrices. There's a subset in black of all product states, and the convex hull is then nothing else than the separable states. Actually, in practice, it looks much more complicated than what you would guess from this cartoon. A huge advantage of these pictures, at least on a formal conceptual level, you can introduce measures, so-called geometric measures of collation and entanglement, namely as the minimal distances to these sets. Okay, in practice, in particular for the entanglement, it's extremely difficult to derive a closed formula, but on a mathematical level, you can just introduce such measures and study their properties. So now let's go back to fermions. So there, the Hilbert space for n fermions is given by the n-fold wedge product of, n copies of the one part of Hilbert space H1. So if you look at it, independent of how creative you are, there's no tensor product between these H1s. And you have, at the end, to conclude that there cannot exist a notion of particle entanglement and particle collation in the strict quantum information theoretical sense, because individual electrons do not define proper subsystems of many electron systems in quantum information sense. So you don't have this underlying paradigm of local operations in classical communications because you even don't have a notion of subsystems. And well, that's not the end of the story, because if you tell this to most chemists or condensed matter physicists, they always come with some but this is not possible. We want to talk about collation, and it doesn't take, it's not very hard to understand what they have in mind. Namely, they would like actually to refer to quantum states which take the form of non-interacting ground states as being particle uncorrelated. And now we can just follow this paradigm of quantum information, just define some sets and later understand what they're good for. So we take the manifold of all Slater determinants, like all the density matrices, which take the form of Slater determinants, and call it just a set of particle uncorrelated states in quotation marks. And then whenever a quantum state is a classical mixture of Slater determinants, then we call it particle separable, again in quotation marks, because we gave up this wonderful quantum information theoretical paradigm of LOCC. Now, by referring to this geometric picture, we can just ad hoc introduce measures, geometric measures, and there are even some wonderful news. Gottlieb and Mauser managed to even derive a closed formula for one of those measures, namely for the total collation. So they found that the minimal distance measured here in terms of the quantum relative entropy is nothing else than the particle hole symmetrized for Neumann entropy S of the 1 RDM rho 1 minus the entropy of the total state. But if you apply this now to pure states, in particular to the ground state, you see it's nothing else than a really simple function of the 1 RDM. It's a second motivation why the 1 RDM is such a wonderful quantity. So now, with with these two informations or two motivations for the one RDM, let's actually merge quantum information and quantum many-body and study some potential applications there. And because of these motivations of the one particle picture, let's actually talk about one RDMFT. Of course, the real challenge is to find a good functional approximation. But before you start finding such approximations or constructing such approximations, you have to understand what is actually the domain of these functions. So for fermions, the domain is essentially described by the Pauli exclusion principle. So you see here, fermionic occupation numbers are bounded from above by the value 1. And for bosons, there are actually no non-trivial constraints. If you have n bosons, in principle, you can place them all in the same one particle state phi. I mean, it's a different question whether this is going to happen in nature or not, but mathematically speaking, it's possible. And now this remarkable result in quantum information theory, to which I also contributed about 5 or 10 years ago, namely that whenever you have a reduced density matrix, for instance here the row 1, which lives on the boundary of its allowed domain. So here in the case of fermions, it would mean you're saturating some of those inequalities, or for bosons, you saturate this inequality, then the corresponding n-particle quantum state has a significantly simplified structure. So again, for bosons, it's quite clear, because if you have all n bosons in the same one particle state, it is just like a quantum state, the so-called Bose-Einstein condensate state. You're just occupying, for instance, a zero momentum state n times. This is your quantum state. But now the point is, this mathematical connection of extremal one RDMs versus structure of the n-particle state directly leads to a property of the universal function. Here, in case of fermions, for instance, you can mathematically show that the gradient of this universal function diverges repulsively on the boundary of the domain. So this means we could actually translate the anti-symmetry of the wave function into a kinematical force in the one particle picture. So for fermions, we call this exchange force, for bosons, Bose-Einstein force. And it actually explains why occupation numbers never live on the boundary for interacting systems. For fermions, you can never have occupation numbers being exactly identical to 0 and 1. And for bosons, you cannot have complete Bose-Einstein condensation. I mean, this is what people already knew. They call it a quantum depletion. But here we provided a geometric explanation for this. And just for the sake of completeness, in case someone is a great fan of functional theory, we found these results as a part of a much bigger endeavor where we discovered at least some abstract forms of these universal functions. And also there it turned out that you essentially need to understand the geometry of the domain of one RDMs. So let me now change to second quantization, to the mode or orbit or side picture. There's a very prominent scheme, namely DMRG, or tensor network approaches, which exploits this simplification. So let me illustrate to you as a recipe how people apply this nowadays also in quantum chemistry the last 10, 20 years. So in the very first step, you identify a one-particle reference basis, for instance, by running Hartree-Fock. Then you arrange these reference orbits on a 1D structure. And now you express your Hamiltonian in second quantization, and then it looks a little bit like a generalized lattice Hamiltonian. So you could apply DMRG, and hopefully it converges, and then you hope to have obtained a good result, right? So now from a conceptual point of view, you could say this application of the matrix product state ansatz is always justified whenever the entanglement between, let's say, the left and the right part of your lattice is much smaller than for generic quantum states. Because this would actually allow you in turn to reduce this huge dimensional Fock spaces for the left and right half to much smaller dimensional subspaces, namely exactly to those subspaces where the reduced states carry their main weight. This is the general idea underlying DMRG. But now, from a practical point of view, you may ask, where is this local structure, or how to choose and arrange these orbits to recover a local structure? And this actually results in the following problem or scientific task. Many people elaborated on this also in my group, and I also would like to share this with you because maybe some of you guys also have some ideas. So let's say I give you such a pattern of orbital collation between any two orbitals, phi k, phi l, is a total mess. So this indicates you made a very bad choice for your reference orbitals. But now the task is to analyze this pattern and to propose an orbital rotation to new orbitals such that this collation pattern drastically simplifies. And the question is a little bit like how to do it. Also, you can ask, what for information do you want to use on the left side? In principle, if you use the whole quantum state, it will be much easier, but in practice, you don't have access to the full quantum state. So there's some trade-off. Then you can also ask, how local can it actually get? So every deviation from this perfect scenario shown on the right side is kind of a signature of electron collation. And then last but not least, you would like to use such a localization scheme not after having found the ground state, but during the course of the process of approximating the ground state. So it's like really like a very general scientific challenge to elaborate on these problems. So let me now again change perspective to quantum information, forget about physics and chemistry for a moment. So here I have very good news. Yes, we can talk about entanglement and collation between orbitals. And the reason for this is entanglement and orbitals are distinguishable, of course. And the recipe for this is straightforward. So you pick your one part of Hilbert space, you split it into left and right part, for instance, in a lattice. Then by using occupation number basis, you see this occupation number states, these ends are all 0 and 1s. You just cut this somewhere in the middle, introduce a tensor product, and this exactly explains why your Fock space, for instance, for a lattice system, a one-dimensional lattice system, can be interpreted as a Fock space for the left half and the right half. So now we should be all very happy because by referring to precisely this tensor product, we could introduce a notion of Alice versus Bob and apply the standard quantum information formalism and talk about collation and entanglement. This is exactly what many people are doing nowadays, and also in quantum chemistry and also my group. And as you can now guess, there are many, many ways how you could decompose your system in two or more subsystems. But as very often in physics and chemistry, the simplest choices are the most relevant ones. And here what I have in mind is, first of all, picking one orbital versus all the remaining ones. In chemistry, this tells you a bit about active spaces because it quantifies how strongly is a given orbital connected to the remaining orbitals. How actively does it contribute to the wave function? Then you can go one step further and can ask, how does this correlation of one orbital with the rest, how does it distribute over all the remaining orbitals? So for this, we would then quantify, for instance, the correlation between orbital I and J. For instance, it could be Hartree-Fock orbitals, could be autonormalized atomic orbitals, it could be lattice sites in the reciprocal momentum lattice, whatever you like. Okay, it's your choice to pick the subsystems. And then we apply this quantum information formalism. But here in my talk, in the last few minutes, I'm going to focus exclusively on those two simple scenarios, one orbital versus the rest, and one orbital I versus orbital J. Just to make sure that we're all on the same page, in practice, we first pick a physical system, then we pick a state of that system, let's say the ground state of a molecule, psi n. Then afterwards, we pick our preferred orbital reference bases, for instance, Hartree-Fock orbitals, and then for any two Hartree-Fock orbitals I and J, we calculate the corresponding orbital reduced density matrix rho ij and the single orbital density matrices rho I. And now what's very crucial to understand is the shape of these matrices or the spaces on which they live. So rho I lives on the Fock space of a single orbital. This is a 4-dimensional space because you have a vacuum state, spin up, spin down, and 2 electrons. And therefore, rho ij, despite the fact that 2 orbitals sounds like a primitive system, rho ij itself is already a density matrix which in principle has 255 real parameters because it lives on a 16-dimensional Hilbert space. Of course, in practice, the rho ij will inherit many symmetries from psi n, like particle number symmetry, spin symmetries, and so on. So many entries in rho ij are 0. But what's also important to understand is whenever I talk about Alice versus Bob, what I introduced at the very beginning, it means we're talking about the rho ij. Orbital I is Alice, orbital J is Bob. So now let's apply it in chemistry. So a potentially interesting question is, what's the covalent bond, and can we use quantum information theory to characterize bonding structures? So we all learned, maybe even during our high school time, about molecular orbital theory. You can say in molecular orbital theory, there's a covalent bond if a bonding orbital is occupied by an electron pair. This does not refer to correlation, right? So let's forget about MO theory. Instead, valence bonding theory is much more naturally connected to quantum info because in valence bond theory, people say there's a bond if two atomic orbits, one on the left, one on the right, whenever such two orbits are coupled or correlated to each other. So our hope is now that we can make this precise through quantum information theory. And in order to elaborate on this, we just applied the scheme to a few simple model systems. So here, like a very linear molecule, where we restrict ourselves to the so-called pi framework, just the pi bonds, and we picked an active space of 10 spatial orbits. And here on the left side, you see these orbits, namely the canonical Hartree-Fock orbits. They're highly delocalized. If you now calculate the ground state of the system, for instance, with DMRG, I mean, it's a very simple system with single reference character, weak correlation, so it's very easy. So if you calculate the entanglement of each of those 10 orbits with the remaining n orbits, 9 orbits, you see these values here for the single orbital entanglement entropies, they're quite small compared to the maximum value that they could attain from a mathematical point of view. This is not surprising, because by quantifying correlation in the Hartree-Fock basis, you do not quantify bonding order, but you quantify the validity of the independent pair picture. So now we thought, okay, that's all clear, so let's try to localize these orbits. And there are many schemes in quantum chemistry to do so. For instance, the Pipek-Mersey localization scheme. So we applied this, and it was a huge disappointment. These numbers didn't grow to the dashed line. And the reason is obvious, because in chemistry, when you apply localization schemes, you still keep the molecular character. So you localize your orbits, but they're still like multi-center, namely 2-center orbits. And to really feel or to really access this bonding character, you need to make them single-center-like. And this is exactly what you achieved by fully localizing them. And then you see these numbers explode to almost the maximum value of log 4. And here, by referring to the small gap to the dashed line, you could actually introduce a very natural measure for electron correlation. And this also emphasizes why the system is so weakly correlated. So now, based on this information here, you may now wonder, okay, how does this correlation of each orbital with the rest, how does it distribute over all the remaining 9 orbitals? So for this, we're going to study now the pairwise orbital-orbital correlation. This is illustrated here, again, for the 3 orbital bases, Hartree-Fock, Pipek-Mersey localized, atomic-like. The first 2 is just like a mess, okay, no structure, because you refer to molecular orbitals. And when you go to single-center orbitals, you see a much clearer structure. You see now all these 2 neighboring carbon atoms are coupled via a black link. And a black link means really like a full, proper, single covalent bond. This is exactly what you anyway expected from chemical bonding theory. And now one last thing I want to present to you here in this analysis is a very funny coincidence or result connecting quantum information and quantum many-body. Namely, when you study now the entanglement, which is a part of the total correlation, there's something remarkable happening on the level of atomic-like orbitals. So first of all, you remove the dirty background, the so-called dynamical correlation. But what's more exciting about this one is that it kind of resembles the so-called monogamy effect of entanglement. So if Alice and Bob are sharing a maximal entanglement state, Alice cannot be entangled with another party, for instance, Charlie. This is monogamy of entanglement. And in chemistry, they also know about this, because if you have an atom, let's say in the middle, a carbon atom, and this carbon atom provides one single atomic orbital to form a bond to the left side and or to the right side, it cannot simultaneously accomplish 2 bonds. To get 2 bonds, you need to offer 2 orbitals. And this is exactly nothing else than the monogamy effect of entanglement. So from that point of view, you could say, if you rotate these orbitals in practice in such a way that you maximize entanglement, a single covalent bond corresponds to log 4 orbital entanglement. And this would actually allow you to quantify bonding orders in practice in a much more unique, more robust way. This is exactly what we did in a recent paper, which we uploaded today to the archive. We followed this paradigm that we're now introducing here to introduce so-called maximally entangled atomic orbitals. And then it turns out, by referring to these reference orbitals, we obtain a very robust universal framework for bonding analysis. So the very last thing I want to present here to you is a link between the particle picture and the orbital picture, connecting the 2 parts of my presentation. You could say the particle correlation turns out to be equal to orbital minimized orbital collation in the following sense. So the distance of the quantum state at hand to the manifold of slate determinants, so we call it particle collation in quotation marks, this is equal to the orbital minimized orbital collation. So here, as we have seen, if you fix a reference basis B, you can introduce this pairwise orbital collation. For instance, here for the chromium dimer with 28 orbitals, you sum up all these links, all these numbers, and you obtain the total collation in the basis B. If you now minimize this over all orbital basis B from Hartley-Fock to Pipek-Mersey localized and so on, then these numbers begin to coincide. So you can interpret this by saying the complexity that you see in practice when you run a scheme based on fixed reference orbitals, it consists of two parts. The intrinsic complexity due to electron collation and an extrinsic correlation due to a suboptimal choice of the reference basis. So to summarize, we shed light from quantum information and quantum chemistry perspective on the particle and orbital picture, and also merge these two perspectives and hopefully could convince you that this interface is very promising and very exciting. Then I presented to you this remarkable link. This is like ongoing. There are many open challenges to be solved and addressed. But let's say if we could strengthen the link between the particle picture and orbital picture, it could have remarkable consequences. It would, for instance, allow us to replace this rather obscure concept of static and dynamic correlation that plays such a key role in chemistry and material sciences almost everywhere. And in addition, and this is of course a never-ending challenge, by having understood what particle and orbital correlations are, and by having found this kind of universal perspective to even quantify them, the chances increase that we could at some point find a more universal, more effective approach to the transit problem. And all of this should be seen even from a broader perspective along the lines of this workshop here. So we have the field of quantum information, we have the fields of quantum chemistry, quantum many-body, and actually both fields, both sides benefit a lot from each other. Quantum information theory provides tools to describe electronic structure, to improve numerical methods. At the same time, all these numerical methods and the understanding of quantum chemistry is absolutely essential to build quantum technologies, which are then used in quantum information sciences for the second quantum revolution. And I think we should foster these synergies more and more in the near future, because these fields are still quite disjointed. So this, I would like to thank you for your time and attention.
Booked online that whichever question you made to ask to Christian, you made to do it through the link that we have shared before. Next, we will have a break, 15 minutes break. We will come back here at, what time is that? 11:25, UTC -6 time, please. See you later. Muy bien.
To everyone in Zoom as well. And well, I will talk about multifractality to explore the quantum classical correspondence in quantum systems. And this is, of course, motivated in the sense that we can employ localization measures, like entropies, to explore the classical phase space via the quantum correspondence. So let me tell you about the talk briefly. I will divide it in 3 parts. In the first one, I will talk about these localization measures, fractality, multifractality, and quantum multifractality. Then I will apply these techniques to a particular light matter system, which is the decay model, a paradigmatic model from quantum optics that describes collective light matter interactions. And finally, in the third part, I will explain how to use these techniques to explore the quantum classical correspondence. And the overall motivation of the talk is to understand more about how the quantum realm is connected to the classical domain. No? We know that there are some straightforward pathways to go from the quantum and classical domain. For example, taking the Schrödinger equation and obtaining the Hamilton-Jacobi equation from classical mechanics. But generally speaking, it's not clear how we cross from one side to another. No? And there are a lot of open questions, for example, on how quantum Nagé states become the specific structures that we observe in classical systems. So the idea here, that's the takeaway message of the talk, is to use quantum localization measures to prove the classical phase space within this quantum classical correspondence. We are going to use a magnifying glass over the classical phase space, and this magnifying glass will be quantum. So let me start with this idea. So the core idea is multifractality. So multifractality was originally introduced by Mandelbrot. You know, this is the Mandelbrot fractal, but he was exploring actually the classical dynamics of fluids. And then to understand fluctuations in turbulence of fluid dynamics, he applied this idea of multifractality. And since then, it has been identified in a vast array of systems from biophysics, like human heart dynamics and brain activity, to quantum physics. For example, this is the wave function of the Anderson model, which is well known because of this idea of Anderson localization. And surprisingly, the wave function in 3 dimensions, it acquires multifractal features when you go from the localized to the localized state. So what is the idea? Let's start with the fractal dimension. So we can imagine an object that occurs in an object and an event that occurs in one part of that object. So if we divide this object into parts, we can ask about the probability of having this event there. And then the idea is to talk about the scaling of this probability. So the more intuitive way to understand it, it's, for example, with the box counting dimension, right? If we have an object in the space, if we have a dot, we associate a dimension to this object as 0, right? Then a line, we make some boxes and we investigate the scaling of these boxes, we will obtain this value. And a figure that is spread on the 2D will be 2-dimensional. So this is the box counting dimension. It tells us what is the scaling of a number of boxes of size epsilon, and how these boxes scale in order to capture the whole object. But we know that there are other objects that are spread in the 2 dimensions, but it's not precisely a 2-dimensional object. No? And this is the case, for example, of the snowflake, Koch snowflake, no, object, which is simply a line where we apply this mapping, this iteration, where in the middle we put a triangle, and in each iteration we have another triangle and so on. No? And we will see that it starts to approach to a 2D object, but it's not. And then if we repeat this box-counting dimension, we obtain, where this is called the Hausdorff dimension or the monofractal dimension, we will have this kind of a value. No? So we say that this is a fractal object, no? Of dimension 1.2, no? Approximately. And then the idea is that, let me check. Yeah, perfect. No? The idea of multifractality is that we can identify several scales of fractals participating in an object. No? So if we have a set of fractal dimension in an object, and these fractals appears in this object, we will speak of a multifractal object. No? So again, we have a probability, and we can build a partition function that depends on this factor q, which is kind of a resolution scale. And then we can ask about the scaling of this partition function. No? And this tau q is called the mass exponent, in such a way that, I have a sign over there, in such a way that for q equals 0, we obtain the Hausdorff dimension that I discussed previously. No? So we can talk about a generalized dimension. No? This is the mass exponent, and this is the fractal generalized dimension. Okay? So in this sense, we can try to explore more complex objects that have different fractals participating at different scales. So, oops, no, there is a problem here in the presentation. No, for some reason, everything disappeared from there. Okay, but anyways, here it was supposed to be the wave function, okay, and the exponents of the wave function. So here the object that we have is that if we have a wave function, a quantum wave function, we can express this wave function in a certain basis, okay? And then this works as a partition function similar to the one I presented before, no? This kind of object, okay? So as a partition function for q equal 1, we will have a normalization condition, no? And this is the same case here in quantum mechanics, no? And we can use this object, which is called the inverse participation ratio, okay, or generalized inverse participation ratio that depends on q, to characterize multifractality in quantum systems. No? And again, we will have a mass exponent that will depend on this object. No? And this is the object that I will explore in the following. Okay. And what is it was supposed to be here some explanation about that. I'm sorry for that. But the idea of the participation ratio is to measure how a wave function is distributed or localized over a certain basis. Okay, that's the idea. And so some people call it a linear entropy. Okay, so if you have heard of rangy entropies, for example, this is kind of a linear rangy entropy. Okay, that depends on this parameter q. And then let me go to chaos, no? Which is another of the important topics here. No? So in classical mechanics, we have that a system is non-integrable in the sense that it doesn't have enough conserved quantities as degrees of freedom, and then the phase space is broken, the tori that constitute the phase space are broken, and we have what is called sensitivity to initial conditions, no? Which is also called the butterfly effect, no? in the colloquial way. No? And the idea is that slight changes in the initial conditions of a dynamical system will lead to different results in the future evolution. No? And there is no universally accepted definition of classical chaos, but we could say that it's an aperiodic behavior at long time in a deterministic system that exhibits sensitivity to initial conditions. No? And classical chaos is super important for a vast array of phenomena like weather forecasting and so on. No? So, of course, because I do not have a lot of time to explain everything, no? Maybe you know that one way to quantify classical chaos is the Lyapunov exponent. No? We can calculate the Lyapunov exponent to assess the instability of the dynamics and understand then if we have chaos or not. No? And then on one side we have classical chaos, we go to the quantum domain, and the question is, what distinguishes classical mechanics from quantum mechanics. No? And then in terms of phase space, we have that on one hand, there is a wave character of the state of the system. And the second one, which is, in my opinion, more important, is the incompatibility between observables, no? That we understand as the uncertainty principle. No? So generally speaking, if we have a quantum system, we can associate a phase space to that quantum system and make a similar analysis, but the problem is that we cannot identify specific trajectories in phase space due to the uncertainty principle. No? So there are no well-defined trajectories for the quantum system. No? And then we talk about quantum chaos. No? An immediate question is, what will happen with a classical system that has classical chaos that we understand very well with the symplectic structure and so on, and calculating Lyapunov exponents when we go to the quantum domain, okay? And this is not an easy answer, and it's at the core of the quantum classical correspondence, no? So in general, quantum chaos will be the discipline responsible for studying what happens with quantum systems whose corresponding classical systems have chaotic dynamics, no? And there are several measures to identify quantum chaos. The most basic is to study the statistics of the energy difference between levels, no? And again, there was a picture here, but it doesn't matter, no? This, for example, this object, it's called the consecutive ratio spacings that allows us to quantify quantum chaos. I'm very sorry about the presentation. No? I was talking about that, no? That it was we can, okay, if there is, if we thought, yeah, because I'm not sure, no? I'm so sorry, but yeah, I have a fail-safe presentation, no, for this situation.
Without chaos.
Well, you know, yeah, I'm expecting chaos, right? So, yeah. So in between, no, the idea is that we have classical chaos and quantum chaos, right? And there is no universally accepted definition for classical chaos, but we understand it quite well. But for quantum chaos, there are more problems because on the one hand, we do not have a precise definition of quantum trajectories in phase space, but also there are a lot of exceptions with the systems, no? And in each domain, we have specific ways to quantify the chaos, no? In classical dynamics, it's instabilities. In quantum mechanics, we use the energy spectrum to quantify the chaos. No, that's the core idea. This is the presentation, right? Yes. Yeah, as you can see, it has low resolution, no? Lower resolution, but it works better, no? Okay, and that's the what. This is the ratio of consecutive energy levels. No, and this allows us to identify if we have chaos or not. We can discuss later in WhatsApp, or you can send me a mail to discuss about this. No, and then the idea, of course, no, going toward the middle of the talk is to explore chaos, no, as a core concept that has impact over a lot of issues, thermalization, quantum information processing between these two domains. Okay, that's the core of the talk. And let me go quickly to the second part. I will use a particular model to study this quantum classical correspondence to apply these ideas, which is the Dicke model. No? This Dicke Hamiltonian was created in the 54 by Dicke, no, by Robert Dicke. Originally, it comes from a light matter description. No, this is a quantum light, a classical light matter Hamiltonian. No, we have the electrical field, the magnetic field, and then we have this series of assumptions, strong ones, that it's a diluted gas, that we have single electron atoms, that the field is spatially homogeneous, that the field cavity is quantized, and the second and the two-level approximation, and with this we have this Hamiltonian, which is a quantum one in an algebraic form. No, you can identify this as the field part, which is the harmonic oscillator, the quantum harmonic oscillator. This is these operators are collective operators that describe the collective degrees of freedom of the two-level systems, no, which represent the matter, no, and follow the SU2 algebra, no, are the angular momentum operators basically, and we have them the frequency and energy of the field, the frequency and energy of the collective set of two-level systems, no, we have these two-level systems, and then finally this kind of interaction where we have a quadrature multiplied, no, by this object, no, and it's kind of a magnetic field. If you recall something about Ising models and so on. No? But this is a Hamiltonian what we are going to use. No? And one of the interesting things of the Hamiltonian is that it was identified in the 73 that if one calculates the thermodynamics of this object, one gets what is called the super-radiant phase transition. No? For some values of the temperature and the light matter coupling, the system basically is uncoupled. And then when one goes to the strong coupling regime, no, actually the ultra strong coupling regime, one gets an emission or an energy that depicts a strong light matter system. No? And if one gets the temperature to go to 0, one gets what is called the quantum phase transition, no? A singularity on the properties of the ground states of the Hamiltonian, no? And this is the critical value. But basically, one gets this expression from the ground state energy, and you can see that this is the quantum phase transition. Here, this is flat, representing that we have an uncoupled system, and suddenly, when one increases the light matter coupling, it appears this super-radiant phase, a major change over the energy of the system. And this will be important because, as we will see, in this regime, we will have a predominance of regular dynamics, and in this regime, we will have the onset of chaos in the system, no? And this is due to the light matter strongly correlated system, no? And this has been a long debated, no? I won't go into the details, but since the 70s, there is a debate of the possibility to observe this super-radiant phase transition, no? Because it also has an impact on quantum optics and quantum technologies and quantum information processing, because it will entail a strongly correlated state that we can access to transfer in a fast way information and so on. No? So in the 211, the system was, or the super-radiant phase transition was realized in an open system. There are some details on that, but then there are a lot of systems, Raman transitions, ion trams, superconducting qubits, where this Hamiltonian can be realized. Okay, so now instead of talking about atoms interacting with light, one could say that the system, the decay Hamiltonian, represents a set of qubits interacting with a resonator. Okay, so also optomechanical systems, polaritons, and so on can be employed like that. And just to give you a broad overview of this, the decay Hamiltonian has a lot of particular cases and belongs to a family of models that share this kind of results. No? This is the Rabi Hamiltonian for a single qubit, the James-Cummings Hamiltonian, which is kind of the major toy model for quantum optics, the AC-star Hamiltonian, the Hopfield Hamiltonian, which is currently used in solid-state physics and atomic physics, and the Travis-Cummings Hamiltonians. So all of them are approximations of or part of the family for the decay model. So most of these results can be exported to these problems. And then a very nice property of the decay model is that one can use coherent states. Okay, that's the procedure. One uses coherent states to calculate the expectation value of the quantum Hamiltonian, and with this, one can get a corresponding classical Hamiltonian for the system. Okay, that's the key idea. So we have the quantum system, and straightforwardly, we can obtain a classical corresponding system. No? There are several semi-classical approximations, and all of them converge to this classical Hamiltonian. And here, I just share with you a picture of what one will get for the classical dynamics of the system. No? There are some structures that one can identify. This is the quantum, the ground state energy, no, that I showed you before. And then one can explore the classical dynamics of this classical Hamiltonian when one goes above in energy and calculate the Lyapunov exponent. Okay, this is for the classical system, and what we'll get that this is regular dynamics, but there is an onset of chaos here in the upper part of the spectrum. So that transforms the model in a very useful model to explore the classical quantum correspondence, because one can access different degrees of chaos as one goes up in the spectrum, no? And mostly in this super-radiant phase. And here is just as a background to share with you the classical quantum correspondence in general. Here is the classical Hamiltonian and the Lyapunov exponent calculated over this parameter space. No? It's the light matter coupling against the energy. Okay, it's the same figure as before. No? And here I'm calculating the percentage of chaos using the Lyapunov exponent, and here I'm using this parameter, this factor R that I discussed before, no? This ratio between consecutive level ratios, and this calculation is for the quantum system, okay? This is purely quantum, this is purely classical. And we can see that there is a nice correspondence, no? Here we have chaos, and here as well, no? This is in the quantum sense, this is in the classical sense, no? There are some fluctuations here because of limitations of the Hilbert space, no? But this is the setup, no? We have this nice quantum classical correspondence, and the idea is to explore the connection in detail, okay? And that's where I'm going with this third part, no? Of the quantum probing of the classical phase space. So the idea is that we can take, this is a Poincare section of the classical dynamics, okay? So of the classical decay Hamiltonian, where we can see that there are islands of stabilities, there is this anistochastic layer where chaos emerges and so on, and the key idea of the method, or what we are going to do now, is to take a point in classical phase space and represent it by a coherent state. This point will be, for example, the coherent state, and this is more or less the ratio of the coherent state over the phase space. And this coherent state, which is actually in this case, because it's a light matter system, is a tensor product between Glauber coherent states, the ones from the harmonic oscillator, and Bloch coherent states, which are the ones from the SU2 algebra. So using this coherent state, I represent a point in phase space, and what we are going to do is to look at how this point is seen in the eigenbasis of the system. This is the eigenbasis, the eigenstates of the quantum Hamiltonian, okay? So I'm looking at this point in phase space via the coherent state, and I'm looking at how it distributes over the quantum spectrum, okay? So this calculation is purely quantum in the sense that the coherent state represents a classical point in phase space, but it's a quantum state, okay? So I'm probing how the classical structure is seen in the quantum domain, okay? That's the idea. And using this idea, no, a first proposal that I worked several years ago was to distinguish between different coherent states. For example, this coherent state has different contributions, okay, over the eigenbasis, and it, let me go back, sorry. No, you can see that, for example, this point is, they are over interchange, sorry. This point belongs to this one, so this is close to a regular or a stable island, and you can see that it's mostly built over, well, it's constituted over a single series with a Gaussian profile. And as I shift from it, no, to the purple point, a series of excitation starts to appear, no? So with this, I can kind of relate information from the classical and quantum domain. And the idea is to calculate the inverse participation ratio, no, that I presented to you before. In this case, the inverse participation ratio is to take the amplitude of the wave function to the fourth instead of the second power, because then it will be the normalization condition. And the idea of this guy is that if we have, for example, 1, it will be a localized state. If we have 1 over n, which is the size of the effective size of the Hilbert space, it will be the localized, okay? So the idea is I take this coherent state, I express it on the eigenbasis, I calculate the amplitudes over the eigenbasis, and then this quantity, okay? And the idea is to employ this Hilbert space localization measure to probe the classical phase space within this correspondence, no? And these are the results, no? I calculate this object. Well, this is the participation ratio, no? The other is the inverse, no? But it's the same. We have here the participation ratio. This is purely quantum calculated over the Poincare section in each point, each coherent state. And we have the Lyapunov exponents. And you can see that the Lyapunov exponents has a nice correspondence between with the participation ratio, no? Here where chaos emerges, no? This is the emergence of chaos. We identify it as an increase of the localization of the wave function over that regime, no? So the quantum, the coherent state representing the phase space structure starts to delocalize over the classical, the quantum domain, no? And here again, no, this is a Poincare section, no? You can see all the complicated structures, no? Here is chaos, here a regularity, and we can use, for example, the participation ratio to mapping, no? To map this and create, for example, a binary criterion, no? This is the Lyapunov exponent, and this is the participation ratio, no? You see that the Lyapunov exponent goes up, no? As well as the participation ratio, no? And so in this way, with the participation ratio as a localization measure, we are probing the classical structures, but from a pure quantum perspective, okay? That's the idea, no? And you see that it works quite well. And then the next idea, I will finish the talk with this, is to work not only with the participation ratio, but with this generalized participation ratio that allows us to explore multifractality, no? And the main point is to see if we can identify multifractal, we can use multifractal information to detect classical structures and so on, no? So we take the classical Hamilton, the quantum Hamiltonian, again, we use coherent states to represent the state, no? And we calculate these max exponents using the inverse participation ratio, no? And we can identify some limits, no? For example, if we have a random Gaussian state, okay, the participation ratio will scale in this way, and if we have a regular state, it will scale in this way, no? And the idea, no, is that in the limit of when the Q tends to 0, we should recover the Hausdorff dimension, no, as we see at the beginning. But then here in general, we will have a general property of these quantum states that, well, no, it's not so important. But here are some results, no? So you can see this is a Poincare section. We have these points that are regular islands, and this is a part of the chaotic sea. And here is the behavior of the mass exponent as a function of Q. And you can see that for this point, which is in this regular island, you won't see more information than a Gaussian. No? We can change the scaling, and we can unveil some structure over there, okay? That is participating in the system. No? But mostly speaking, from this point onwards, the mass exponent behaves just like this blue line that represents a regular or one Gaussian state. Okay? There is some deviation here, but we can talk about it if you want. No, this just so you can look at how, no, the structures are unveiled for a kind of regular state. No? And then we go to this point, which is in the chaotic domain, no? Where chaos emerges in the system, and you see that now the wave function of the coherent state, no, it starts to distribute over the eigenbasis, no? And if we change the Q, we can change the resolution for us, and as well we can calculate this, and we see that now it goes to the red line, which is closer to ergodic system, something that delocalizes completely over the Ferri space, no? So we have this nice quantum classical correspondence, no? And we can try to make an approximation to linear, no? A linear system, no? To see how it behaves, or understand weak multifractality. And you see that we can follow, no? By calculating the generalized dimension, no? In this line, these points, we see how it goes up and down, just as the participation ratio was, no? But also we have some changes on the nonlinearity of this object that indicates the presence of other structures. So by changing this quantity, we can prove the classical structures quantumly and unveil different features in the phase space. No? And there is a challenge here that the decay model is a system which is unbounded, so one has to numerically be careful. No? And just to end, no, you see that this is a Poincare section for a chaotic sea, a fully chaotic sea, and still, no, for example, this point over here, the measure is sufficiently sensitive to identify, no, this kind of structure. No, this is a particular state where you can see that it's mostly localized, no, this object, and then, no, it remains localized. So what we can see is that it goes like this, and then the localization goes to 0, no? And this is a way to detect a kind of fixed point in the mapping, in the dynamics, no? So this is kind of finite size multifractal behavior, no? And just to conclude, no, the decay Hamiltonian has been used as a general formulation for the spin-boson interaction, no? There are a lot of realization for various systems, and also it allows us to make this nice classical quantum correspondence. And with this quantum refractality, we published it in Physical Review E last year, no? We can prove the system, no? And currently we are assessing many questions about this tool in other kinds of systems, such as kicked systems in time and so on, no? And with this end, I finished with my group here at the physics department at UAM Iztapalapa. No, there are the Ernesto, a postdoc researcher, several PhD students, and so on, and also some marketing for upcoming events. No? We are pushing forward a community on polaritons, which is light matter interaction. No? This event, the Ethic Lawili Polariton meeting. No, we had 2 years ago the first meeting, then a polariton school, and we will have this year another meeting, international one, no? If you are interested. And with this, I'm finished. I'm sorry if I take a lot of time. And if you have any questions, you can send me a WhatsApp. No? I'm in the group. Thank you very much.
Thank you, Miguel. So we have 1 minute time for questions.
Well, if you have questions, you see this fractality.
Okay, no question, we end the speaker and continue with the next. Thank you, Miguel.
Yes.
Okay, please prepare. So the next speaker is Adrián Escobar, and he will speak about the version of spatial and magnetic confinement, superintegrability, information theory, and neural networks. Please, Adrián.
Okay, so thank you. Welcome everybody for joining me today as I speak about this hydrogen atom under spatial and magnetic confinement. So the idea is just to explain how we can use tools from superintegrability, information theory, and neural networks to study these kind of systems. So the plan of my presentation. Okay, so this is the overview. So 3 parts. In all of them, I'm going to use the hydrogen atom to explain, to review what is superintegrability, localization, and Shannon entropy, and finally this the use of artificial intelligence to study the systems. Okay, so let me start with this nice quote from Richard Feynman, who said that atoms, they are very special objects. They like certain particular partners, particular direction, and so on. And it is the job of physics to study, to understand why each of them wants what it wants. So for me, this is a very nice answer to what we are doing in physics. And the main object or the main system I'm going to talk about is atoms and molecules under spatial and magnetic confinement. Why? Because they act as a bridge between what we can say it's fundamental research in quantum mechanics and cutting-edge technologies. So this is one of the motivations. So I will be focused more on the fundamental part rather than the technologies. And of course, actually this year we are celebrating the International Year of Quantum Science and Technologies. So another important motivation to consider those systems is the number of relevant applications they have in different fields. Nanotechnology and quantum devices, it's well known that atoms and molecules are good candidates to be this, to form qubits, no? In this quantum computing. In astrophysics, we have models of atmospheres in neutron stars, even our planet. And in those models, very basic ingredient is atoms and molecules under some extreme conditions sometimes. Of course, in chemistry and also in biology. So, and this is not a field that somehow it's in the past. Actually, it's a very growing field, and the most important fact is the experimental evidence that we are getting every day. So, more or less 2 weeks ago, this nice paper appeared in Nature. So, excitons in fractional quantum Hall effects. So, excitons are quasi-particles. Usually, we can think about them like kind of hydrogen atom, but instead of electron and proton, we have electron and a hole, and usually they carry integer electric charge. But now this is the first time in the lab, because they already were predicted some time ago, but this is the first time that people can measure, can see excitons, but here the basic constituents, they carry fractional charge. So fractional electric charge, and this is absolutely remarkable results from the experimental point of view. Okay, so now let's move to the main equation I'm going to consider. So this is the spectral problem defined by the Hamiltonian operator, so time-independent Schrödinger equation, and we have the main objects, so the wave function, and also the eigenvalues. Of course, spatial confinement enters into the game in affecting the boundary condition of this equation. So what's the goal? Or let me remind some key general questions we want to somehow to answer in this system is how the spectrum, how the eigenvalues and also the wave functions evolve when we change the external parameters like magnetic field or the size of the boxes. So how these two objects are changing with magnetic field and parameters. Of course, in the morning we heard a lot of other interesting questions like spatial correlation, entanglement, and so on. In particular, also transport properties. So let me focus on the first two. And of course, how we solve this rather, for many electron system, rather difficult equation. We can take a good software, a good computer, and just do numerics and get results, right? This is a straightforward method. However, if we follow that strategy, usually we don't get the physical picture in a clear form. So we get results, but the physical underlying phenomena, somehow it's hidden in those numbers. In this talk, I'm going to describe an approach to solve the Schrödinger equation, but we want to combine tools from, as I said, superintegrability, information theory, and neural networks. Okay, so let's just review very basic facts about superintegrability. Why we are interested in that concept? Well, because already Wolf and Pauli noticed that using algebraic group theoretical methods, we can avoid solving the Schrödinger equation and get, for example, the spectra and eigenfunction of superintegrable system. So this is a very elegant and nice property of those systems. Even Peter Higgs, this famous physicist, he was interested in superintegrable system, and he solved somehow the hydrogen atom on the sphere. In our case, this is the most elementary Hamiltonian we consider in atomic physics, the free hydrogen atom, kinetic energy, Coulomb interaction. And in any standard book of quantum mechanics, we can find the solution of the Schrödinger equation, usually associated with the symmetry SO3. So we're using spherical coordinates. These are the eigenfunctions, but for our purpose, it's better another representation presented here. So we replace spherical coordinates by, we keep r, but then we introduce this coordinate u, which is nothing but rho squared. Rho is just the cylindrical distance, so to the squared, and we keep also the azimuthal angle. So this is another representation, and if we ask how the exact solution look like, this is the answer. So we have another quantum number P associated with parity under C reflection, and M is the standard magnetic quantum number. What is nice is that also here in this factor is nothing but a two-variable polynomial function, right? So why we said, or why this problem has a hidden symmetry, it's superintegrable, is because we can indicate clearly 5 integrals of motion, so 5 quantities, which commute with the Hamiltonian. They are pretty well known. We have angular momentum, also Laplace-Runge length, vector, so they are operators, but vectorial operators. So we can easily check that they commute with Hamiltonian, and in fact, it seems that there are 7 integrals of motion, but there are 2 constraints. So we have 5, which is the maximum number of possible integrals in a 3-dimensional hydrogen atom. So it's maximally superintegrable. This is the algebra they satisfy, so it's also pretty well known. And unlike a standard Lie algebras, this is quadratic. So we have here a quadratic term in the commutators. So probably it was Fock the first who noticed that this is not a Lie algebra, but quadratic Lie algebra. Sorry, it's not Lie, it's just quadratic. Okay, so the application of this is how superintegrability enters into the game. Now we take the hydrogen atom and we put a magnetic field. It's not anymore a superintegrable system. Actually, the classical case is a chaotic system. However, if we consider a constant magnetic field, so this is how the potential will look like, Coulomb plus magnetic interaction, the representation we're using is still valid, so we can take this function, and moreover, the problem to solve the differential equation, this Schrödinger equation, becomes algebraic. If we implement perturbation theory, we use this nice property of superintegrability to reduce differential operator, just a pure algebraic task, which is simpler. So this is how superintegrability enter into the game. It simplifies the task of solving the Schrödinger equation. Okay, since this is a meeting where physicists, mathematicians, and chemistry they are involved, let me just give some few remarks which I think are relevant for the mathematicians. One is related with nodal surface. So we have this theorem by Courant, no? It can be found in the book, which tells us that let's take the nth level eigenfunction and also order the corresponding eigenvalues in this form. So the number, the essence of this theorem is that the number of nodal domains of those wave functions satisfies this condition, right? So this is it gives, it relates the number of nodal domains with the quantum number labeling the states, okay? Let's take a picture of, let's see a picture of the hydrogen, in the case of hydrogen atom. So this is the standard probability density. It appears everywhere in any book. So usually people is looking at these regions, but with Courant, the perspective is different. We want to actually to find these obscure regions. Obscure region is more or less where the electron is not, is absent there. So it's a different perspective. In this, for those states, nodal surface are this, they have this spherical symmetry, right? Of course, this is not new. Already, Vladimir Arnold in '89, he posed a very nice problem regarding the nodal surface of the hydrogen atom. Up to date, it's still unresolved, so it's not easy to solve, but it was posed by Arnold. Just to give you a more example, for in one-dimensional case, nodal surface is just 1 point, and it captures all the information by the Sturm-Liouville theorem. In 2 dimensions, we have nodal lines, but in a 3-dimensional physical space, we want to find the nodal surface. Okay, In this second part, let me just take a very concrete system and to apply these kind of ideas. So this system is nothing but the hydrogen atom with magnetic field, and in addition there is an infinite cylinder, and the electron cannot penetrate the cylinder. This is the corresponding potential. So we have the superposition of three non-trivial interactions: Coulomb, magnetic, and also the confining potential. I will explain in the next slide. So this is the first term, the Zeeman effect. It's written here, and we use what is called the symmetric gauge. In all presentation, I'm going to use atomic units, so h bar and all those are equals to 1. So this is the picture of the system. We fix the proton in the geometrical origin of the figure. The electron is here. This is the cylinder. There is an actual constant magnetic field, and the relevant quantities also are presented. The radius of the cylinder, so this is external parameter we can somehow control. This is ρ0, and ρ is the radial variable. We can model this surface using this function. So the potential is 0 inside of the cylinder, and outside it's infinite. Okay. To solve the Schrödinger equation, let's use a very standard method, which is variational method. And let me describe the three main ingredients of our trial function. The first three terms, they come from superintegrability. We have eigenfunctions of parity operator, eigenfunction of LC, and this comes from asymptotic behavior at small distance. So this part, it's very general. The third part actually is very, I would say, standard in literature. It's called the Coulomb orbital, ground state of the hydrogen atom without magnetic field, and also the Landau orbital. So they are pretty much known in molecular and atomic physics. A novelty of the present study comes here in the second factor. This factor, it's somehow the role of this factor is to ensure that wave function vanishes at the boundary of the cylinder. And it's called cutoff factor, and the novelty appears here. In many, many papers you can find on the web everywhere. This factor actually sometimes there is here 1, 2, 3, and people can just change by integer number. But here the idea is different. We are not going to fix a priori this parameter and promote to a variational parameter. The same like alpha and beta. And all of them, they have physical interpretation. Alpha is it measures the interaction of electron with the proton, and beta, of course, with magnetic field. And now this new in some sense, variational parameter governs the form of the cutoff factor. Okay, so this is very simple function. And so let me emphasize this point. In this study, the goal is not to get benchmark results, but for the first time to identify among an infinite one parametric family of cutoff factors, what's the best form of the function. And how we select the optimal form is by minimizing the energy. So it's in parallel with variational method. We look in the literature, to the best of our knowledge, surprisingly, nobody has somehow introduced a genuine variational cutoff factor in atomic and molecular physics up to now. And this is not just a fancy artifact. I'm going to show that with that very simple function, we get much, much better results than standard, more complicated approaches. This is just the behavior of the expectation value, so the transversal size of the atom as a function of confining radius and magnetic field. So everything is smooth as it should be. the same can be done with this ratio. This is transversal, and this is longitudinal distance, also as a function of the magnetic field, confining radius. It's smooth. The energy, of course, the energy of the system. We can see that for somehow large distance of radii at 5 and 0 magnetic field, we recover the well-known -1/2 of the hydrogen atom. Okay. Now, since this workshop or this event is, many people will talk about informational measures. I'm just going to present one slide. This is the Shannon entropy of the system in position space. So this is the expression we use to find the numbers, and in terms of as a function of magnetic field and also the radius. No, this is a standard. It helps us to, together with the other expectation value, to give a precise, with numbers, characterization of delocalization of the system when we change this parameter, magnetic field and the size of cylinder. But now, does it make sense to promote this nu to a variational factor, or is just more numbers? And the answer is no. Actually, it captures a very deep phenomena. Let me just give some examples. For 0 magnetic field, you can find in this to reference. So people already calculated. This is not new. This is the ground state energy for 0 magnetic field with a cylinder of radius of 1 atomic unit. The result is this, but using the trial function I just presented, we get this number in blue. And we can see that the difference actually appears not in the 4th or 5th significant digit, but in the 2nd one. The same happens for other values of the cylinder. And we can also do the same with non-zero magnetic field. Let me just focus on B equals to 0.4, just for simplicity, and compare with a standard approach use it in this problem. The standard approach, we take Landau problem alone. We solve this exactly solvable problem and multiply by somehow a Coulomb factor and then make minimization. So this is also pretty well known. If we compare those results with the ones we can derive using our trial function, we see a better improvement in 8, 34, 70, and 2% at these values of the radio. No? So even for 0 magnetic field, non-zero magnetic field, a very compact function can provide results almost in the other case was almost 40% better. No? Okay, now the last part of my talk, it's related with these neural networks. I just presented the variational method. We have 3 parameters, alpha, beta, and nu. And the idea would be to have an analytical approximate expression of those 3 parameters in terms of the magnetic field and the size of the cylinder. For that, of course, we need to calculate more points. It means more computational time, more efforts, and actually it's very boring, right? So what we have in mind is, okay, just compute representative points and then take this neural network, which is nothing but a very nice box, which is tool to recognize patterns. They're very powerful, and just train the neural networks to give you more data. With that data, now it's easier to get or to interpolate analytical expression. So at the end, you will end up with this trial function, but alpha, beta, and nu, they will be analytical expression. And it will, there is a accuracy of 3-4 digits, which in the non-relativistic domain is the answer of the problem, right? Because we cannot expect more accuracy using the non-relativistic Schrödinger equation. So I'm not going to talk about all details. It was already done in this paper with some collaborators in UAM. No, it was published, I don't remember, just 2 years ago. And in that case, we don't use the same system, but we allow a different potential. So we replace the cylinder and magnetic field by this inverted Gaussian function, which is interesting from different points of view. It's already, so this is the expression, and this is the corresponding Schrödinger equation. So just let me give you this structure or the Redal neural network we used. Is just presented here. So we calculate some points, then train the neural networks, and at the end we get a lot of data to construct the interpolation of either the energy of the variational parameters, if that would be the case. And we can see, we checked actually that the accuracy of doing this procedure using this technique or standard is much better. No, not only in time but also in the quantities. Okay. So just let me give you some conclusions and remarks. We take this standard system, hydrogen atom with cylinder and magnetic field, to illustrate a program where we can combine 3 different somehow approaches. One is superintegrability, second was information theory, and finally neural networks. They allow us to study in a, I would say, more unified way the dynamics or the behavior of quantum system under external conditions. There are here some, in addition to the original reference I gave in the first slide. Let me just mention these 6. So we have classical works of confined many electron systems. Also, one of the speakers, Khalida Sen, will talk, I think, on Friday. Also, Professor Lei Ku. There is a recent review paper on confined atoms, and I would actually emphasize that UAM has played a very important role in the field of confined systems. So it's a very pleasure to mention that we are somehow at home. Some researchers made important contributions. And with that, I want to finish my presentation. So thank you.
Okay, we'll now have a 10-minute coffee break. So we'll see you in 20 minutes. 20 minutes coffee break, and we will be back with Jorge Bolaños.
Okay, let us resume. Welcome everybody to this second part of this session. Next speaker is Jorge Ricardo Bolaños Servín from the Mathematics Department in UAM Iztapalapa, and he will speak about entropy production rate of quantum Markov semigroups. So please, Jorge, go ahead.
Thank you, Roberto. Well, I'm very glad to be participating in this symposium. I would like to thank the organizers So for me, it was it was an interesting thing to think, a good topic to share with you in this symposium. And after considering the wide range of topics that this symposium was covering, it reminded me of this of the entropy production rate of quantum Markov semigroups, a work in which we worked some years ago, me, myself, and Roberto Quesada. So I think this is a nice opportunity to share with you this. So, okay, so this is a joint work with Roberto Quesada Batalla from some years ago. And the overall overview of my talk will be the following. So I want to give a brief motivation of the entropy production rate in the classical context, that is in the Markov chain context. Then I will cover and explain a little bit of the obstacles when going to the quantum case. So I'm going to discuss some notions of quantum detail balance. And finally, I will define and show some results on the quantum entropy production rate for quantum Markov semigroups. So let's begin. In the classical case, in the context of probability, precisely, from an irreducible Markov chain with finite state space, well, we know that in this case, finite state space and irreducible, the chain has an unique invariant measure, which I call pi over here. Let me see. Yeah, I can do this. And the infinitesimal generator of the generated semigroup, it's called Q, or the so-called Q matrix of the Markov chain. So in these settings, it is well known that one can define a reverse chain. So this basically is the chain with the arrow of time going in the opposite order, also called adjoint. And this is defined with respect to the invariant measure. So this is the adjoint chain with respect to the invariant measure pi. And so this gives rise to another continuous time Markov chain with generator Q minus. In this setting, if I denote by PT and PT minus the distributions of both chains restricted to the interval 0t, then since they are probability distributions, I could think of how can I measure the difference, the probabilistic difference between these two distributions. Why I am interested in this? Well, because that's precisely what reversibility means. Reversibility, we say that a Markov chain is reversible if the process is indistinguishable from the reverse process. So that's the main interest of, in some sense, measuring the difference between these two probability distribution at each time t. Well, the restriction in each of the intervals. How can one do this? Well, the most natural thing is to use the so-called relative entropy or the Kullback-Leibler divergence, as many of you will know, which is defined in this way. Is basically the integral of the logarithm of the Radon-Nikodym derivative of these two distributions whenever it exists, and it is integrable, of course, and it's infinity. It's defined as infinity in other case. Now, from this, one can define the quantity that we are interested in this talk, which is the entropy production rate. The entropy production rate is thus defined as this quotient, is the limit when t goes to 0 from the right, of course, of this quotient, the quotient of the relative entropy over t. Essentially, we are computing the derivative at 0 of the relative entropy of these two distributions. Okay, so this is the classical scheme. Let me go to the next slide. Okay, so let me recall. Reversibility means this process is indistinguishable from the probabilistic point of view from this other process. And so it is well known that there are some equivalent conditions to the reversibility in terms of the well-known detailed balance, which is this condition over here, or also the Kolmogorov criteria, which is a condition on finite collection or cycles. One can also define it in terms of cycles, meaning that the Q are the matrix elements of the generator Q. So these are the intensity transition of the chain. And whenever this equality holds for any finite collection, then we have detailed balance and we have reversibility. And it turns out this was studied by Qian and others. They gave this equivalent condition in terms to reversibility and detailed balance and Kolmogorov criteria in terms of entropy production rate. So the condition is the chain is reversible. It satisfied the detailed balance condition and the Kolmogorov criteria. If and only if, well, there's an if and only if between each one of these conditions, the entropy production rate of the chain with respect to the invariant measure vanishes, equals 0. So we have this condition. And this is the condition that I would like to expand on in this talk, but in a more general setting, in a quantum setting. Okay, so let's go. Let me give you a brief example of this in this context. So let me take a particular type of Markov chain. Let me take a circular Markov chain, that is a Markov chain of dimension p with p finite with p states and with the Q matrix given by a circular matrix, namely the one that you are watching on your screen now. In this case, one can check that if the alphas, if these parameters are such that the chain is irreducible, you can always find this case. Then this is the unique invariant state, which is essentially the uniform distribution in a set of P in the state space. And after some computations, one can obtain that the entropy production rate is given by this quantity. It's a nice expression, as you can see. And when one wonders when this entropy production rate is 0, then so that the chain with respect to the invariant measure pi satisfy the detailed balance condition or the process is reversible, then the condition that one obtains is a symmetry condition on the parameters, on the intensity transitions alpha. Okay, so again, this is a nice example where we have a symmetry condition, very nice symmetry condition, which characterizes the reversibility of this process, which is a continuous time Markov chain, well, continuous time circulant Markov chain. So what can we say in the case of a quantum Markov semigroup? Why quantum Markov semigroup? Okay, so let me briefly recall what is a quantum Markov semigroup and why we are interested in this object. Given a Hilbert space, let me consider the generator of a uniformly continuous quantum Markov semigroup. So which, okay, there should be here an equal. I'm sorry, this is a mistype. Which I'm presenting this in the Schrödinger representation. So I'm talking, I'm presenting this in the states representation of the process. The generator of quantum Markov semigroup, which is essentially a family of a semigroup of uniformly continuous semigroup of completely positive maps and trace preserving maps, so channels. The generator in this case has the well-known Gorini, Kosakowski, Sudarshan, Lindblad form, which is given by this expression. And okay, this type of object describes the evolution of an open quantum system via the well-known equation over here. And we recall that a state is a bounded operator, positive bounded operator with trace 1. We say that the state is invariant for the generator or for the semigroup if is a state and it is on the kernel of the generator given in the Schrödinger representation. Of course, one could always define these objects in the Heisenberg representation, which I denote, so the Schrödinger I denote with a small asterisk here, denoting the predual. So, but okay, I will be mixing both notations in different moments of the talk. So I'm interested into what can we say about quantum entropy production rate, or let's say reversibility, for this type of process. And this is the first obstacle. Why? Because there's not a single notion of detailed balance. We can find at least 3, but I remember I saw more of them, and it was a topic of heat and discussion some years ago. So let me present to you a few of them, and I will tell you which one I will pick for my study here. So given a faithful invariant state of the generator, one can define a family of maps through this duality relation. So for any S, we define the adjoint for each T, we define a map, tau of T with superindex S, and we call it the S adjoint through this duality relationship. So this is the generator satisfying this equality for all x, y bounded operators on the Hilbert space. Notice that S here, what we are essentially doing, we are decomposing the faithful invariant state into this part, into row of S and row of 1 minus S. And so we have a wide family of maps over here. It turns out that one can see that there are essentially 2 relevant cases. One of them, which I shall call the quantum detailed balance, is recovered when S equals 0. So the state, the faithful invariant state, is not decomposed. It's only in this part. And with this type of setting, one obtains a type of, the S equals 0 adjoints. And one say that the semigroup satisfies the quantum detailed balance condition if the 2 semigroups coincide. The semigroup, the original semigroup, and the S equals 0 adjoint. So this is one notion. I could expand on how this condition is looked at the level of generators, but I will not. I will focus only in the semigroups. Second notion that I want to present, the so-called standard quantum details balance condition. This is recovered when we choose S equals 1.5. It's the second meaningful case that I previously spoke about. This condition, so when S equals 1.5, we obtain another type of S adjoint over here, defined again by the same duality relation. And we say that the standard quantum detail balance condition holds again if this semigroup, these maps, equal these other maps over here. Now, the duality relation that we obtain with S equals 1/2 reminds, or is precisely the condition known as Kubo-Martin-Schwinger symmetry, or Kubo-Martin-Schwinger condition. So that is why it is natural to call this S equals 1/2 adjoint the KMS adjoint of the semigroup. So this is a second type of notion of a quantum detail balance. And there's a third type that I want to introduce. And to do that, I want to incorporate the property, the quantum property, as known as the parity of observables, which, okay, has been widely studied by many, for instance, by Agarwal. Essentially, the parity of observables, in order to recover the parity of an observable, one has to define a time reversal operator. So what is a time reversal operator? Here, big theta. A time reversal operator essentially is a map implemented by an anti-unitary operator. So here the small theta is an anti-unitary operator. And from this one can define what does it mean for an observable to be even or odd. I will not include this in my talk, but one can incorporate this into one of the previous notions of standard quantum detail balance. And this was done, for instance, by Fagnola and Humanità. And this is called the theta standard quantum detail balance. So we are mixing the standard quantum detail balance with the notion of parity of observables into the quantum detail balance condition. So basically, we are obtaining a third notion, which is the theta standard quantum detail balance. Again, it's the same with S equals 1/2, but with the parity of observables incorporated. And we say then that a semigroup admits a theta KMS adjoint whenever there's a map satisfying these duality relations, where you can see that first, the invariant state is decomposed with S equals 1/2, and there's a time reversal operation in both sides of the duality relation. We say that this condition, theta standard quantum detail balance condition, holds if these two maps are the same. After some technical assumption, one can also obtain that the maps obtained in this way form also a semigroup, and they have a generator associated. So we are comparing two semigroups. Okay, so some authors argue that this quantum detail balance condition is the most natural quantum extension of the classical one. And so this is the one that we decided to follow in order to, in some sense, find a characterization in terms of some type of quantum relative entropy. So the next natural step is how can we somehow measure this theta standard quantum detail balance condition? The natural thing is to look back and, okay, what did we do in the classical case? We used the relative entropy. We have, in the quantum case, an analog of this, which is the von Neumann relative entropy for states, which is defined, as you can see. So the quantum relative entropy, or von Neumann relative entropy for two states, eta and sigma, is defined as the trace of this quantity whenever this condition is satisfied, infinite in any other case. So the problem now is, how do we measure the relative entropy of these two semigroups? Because these objects are semigroups. And the quantum relative entropy measures, it's defined for states. So one possible way would be to choose an initial state, let's say eta here. And from there, one can see how does the evolution go in one direction, let's say, and how does the evolution go in the other direction, and measure the von Neumann relative entropy in this case. But this is, there's something that bothers us, which is that this is dependent on the initial state. So we would like to somehow use the relative entropy in some state which has the information of both the semigroups and, of course, the initial, the invariant faithful state, but without depending on an initial state eta. And so this is how we decided to tackle this problem. You will recall the celebrated Choi-Yamukowski isomorphism, which gives for each, okay, here I think this shouldn't be an X. I think this is, I don't like this X. This should not be here. So for a given channel, one can associate a state in the tensor product by tensoring with the identity and choosing sorry, there was a spot here on my screen. By tensoring with identity and considering the maximally entangled state here called omega. So this is the well-known isomorphism that for each channel gives a state in the tensor product. We used a variation of this isomorphism, but we're going to change, instead of using here the maximally entangled state, we're going to use a raw entangled state. So by using the diagonalizing basis of the faithful invariant state rho, we are going to weight this entangled state with these weights, which, since rho is a state, this is well defined. And thus, since every object in of these semigroups is a channel, is a completely positive trace-preserving map, then using this modified Choi-Jankowski map, we can obtain states in the tensor products. And these states, notice that these states, which I call here E rho for tau and E rho for tau theta, and this is for each t, I'm obtaining here a pair of states, yes, in a bigger space in the tensor product, but they have the information of these evolutions, and they have the information of the faithful invariant state of this evolution. And this kind of resembles what we had in the classical case. So it is only natural to study this quantity over here. And after doing so, one can obtain this nice theorem, which says that given a uniformly continuous quantum Markov semigroup and a faithful invariant state with a technical condition over here, which we need that the range of this state is all H in order for the map to be injective. Then we can state that the semigroup satisfies the quantum theta standard quantum detail balance condition if and only if the von Neumann relative entropy of these two states equals 0 for all t. So this looks like a much stronger result than the one we were hoping for. But okay, let's continue in this path. So this resembles the classical theorem, but it's quite stronger. Following the same direction, we can define the quantum entropy production rate for the semigroup and the faithful invariant state rho as the limit of this quantity. And so, at least for now, we have the following analogy. So in the classical picture, we had Markov chains, stationary measures, detailed balance condition. We have a generator of the reverse process. We use the relative entropy for the distributions of both chains. And from there, we define the entropy production rate, characterizing the detailed balance or reversibility in terms of entropy production rate equals 0. In the quantum case, what we had so far is a quantum Markov semigroup, a stationary state, faithful stationary state, this theta standard quantum detail balance condition, a generator of another semigroup. We have some states in the tensor product via the Choi-Jankowski modified Choi-Jankowski map. We consider the relative entropy of these two states. From there, we define the quantum relative entropy, and we would hope that this quantum relative entropy somehow characterizes the theta standard quantum detail balance condition. So is it true that this happens? Well, it turns out that this is false. And this was very surprising for us some years ago. Probably you can find many examples now in the literature in that period of time that this was the one that opened our eyes. So this is a really simple example. So you can see that this is an example on a Hilbert space of the main dimension 2. One can consider the generator given by these Krauss operators with this Hamiltonian. And well, after some computations, I'm going to spare you the big computation. You have to compute several things over here. But one can see that the normalized trace is a faithful invariant state of the semigroup. Also, one can check that the theta standard quantum detail balance is not satisfied. But after some tough computations and computing the quantum entropy production rate of the semigroup, with respect to this faithful invariant state, then the limit equals 0. So we have quantum entropy production equals 0, but the theta standard quantum detail balance condition is not satisfied. So this was really a bad news for our hopes. So we could not expect to get the same type of results for quantum Markov semigroups. But it turns out that not everything is lost. Why? Because at that time, we were also studying a particular family of quantum Markov semigroups. And here, let me introduce you to the circulant quantum Markov semigroups. So a circulant quantum Markov semigroup is a family of quantum Markov semigroups with a special structure. So the structure is given by this in this form, where the Krauss operators here, the JP, are given by this, essentially this matrix and the powers of this matrix. So we have cyclic shifts of the reference basis, let's say the canonical basis. And in this case, again, when the alphas are chosen properly in order, well, you can choose it in such a way that the associated Markov chain is irreducible. Then one can observe that rho, the normalized identity, so the trace state, is a faithful invariant state of these generators. And the theta standard quantum detail balance condition holds for this type of semigroups if and only if this symmetry condition is satisfied, which is familiar to us at this point. On the other hand, using the Choi-Yamukowski isomorphism to each one of both the semigroup and the adjoint, getting the states in the tensor product, and then computing the quantum relative entropy of these two states, one obtains a quantity this fashion. Here are some computations that have to be done. A lot of the structure of circulant matrices is used in order to simplify these computations, but one can compute that the entropy production rate of this family of semigroups is precisely this quantity, which again is familiar to us now, because this quantum entropy production rate equals 0 if and only if this symmetry condition holds. So what we are obtaining is that there are families, this is one of them, where the entropy production rate equals 0 satisfy the theta quantum detailed balance condition, just like the classical case. But we cannot hope to obtain this type of characterization of the theta standard quantum detailed balance condition in terms of quantum entropy for every quantum Markov semigroup. Again, let me point it out. For this family of semigroups, the circulant quantum Markov semigroups, if one restricts the action to the diagonal family of matrices, one obtains a classical Markov chain, and this chain is precisely the one that I gave in the first example that I talked in this presentation. So hence, this may not be as surprising, but again, it's interesting to see that at least for this family, quantum entropy production rate equals 0 characterizes the theta standard quantum detail balance. I think, okay, I would like to stop here in case there are some questions. There are some, I have some references here, and well, thank you very much.
Okay, thank you, Jorge. We have 5 minutes. If there are some questions or comments, please. Well, if no question, no comments, so we thank the speaker And we go to the next speaker in 5 minutes.
Thank you.
Thank you, Jorge. Next speaker is Rocío Jaúregui. Is Rocío there?
Yes, I'm here. Can you listen to me?
Yes, I can listen. We hear very well. You get ready, Rocío. Rocío, please try to use the full screen mode because your slides look very small. Full screen. Okay, next speaker is Rocío Jaúregui, and she will speak about variational approach to time-dependent systems, surface tension of quantum droplets. So, Rocío, please. If you try to set the full screen mode, please, because your slide are rather small. Okay. Okay, Rocío. We are ready to listen you.
Está muteada. I can hear.
I can hear you, Rocío. Please turn on your microphone. Hello, Rocío.
Okay.
Very
Now?
good.
Sí,
No,
yes.
go ahead.
Again, sorry. It's a nightmare. Okay. Thank you very much for being here at this interesting talk. I want to celebrate the 15th anniversary of UAM because you have worked a lot during all these years. I have seen that at a distance, from a distance, but congratulations. Today, I will give a brief summary of recent advances in the description of quantum droplets. I will say what a quantum droplet is. I will try to give information about the latest results, both theoretical and experimental. And more importantly, at the end, I will try to make a connection with what I think would be useful to take from information theory to have a deeper understanding of the results. Okay? In general, a droplet has many properties that attract the attention of even a small child. It is a state of aggregation of matter in the form of a highly incompressible fluid that is self-trapped. That means that you don't have to put an external field or container to confine it. So droplets, even if you have had a baby, you notice that water is very important for a baby because they see this and they can imagine, they notice that it is different from the rest of anything. The liquids in general arise when you have a balance between interactions of the particles that form that liquid, and this kind of interaction can be either intramolecular or intermolecular. Any of them has an electrostatic origin and in general is described by natural induced or induced multipoles. To have a liquid, you must have a minimum at a certain distance that guarantees that the system stay close to each other, okay? Now, a droplet has a different something else than any liquid, and it arises from the tendency of being self-trapped. And Raleigh noticed that this self-trapping should be described in terms of the energy, the tension, the surface tension, which is defined as the amount of energy needed to increase the surface of a droplet. And quantum droplets arise when you have a system that is a liquid, but you require, for understanding its dynamics, only quantum aspects. Of course, any liquid is described by quantum theory, because you can put the Schrödinger equation, you can put the interaction between the atoms and the molecules and see the fluid and see the behavior of a fluid. But in general, one will talk about a quantum droplet when something behaves like a liquid, even if it is not a liquid. For instance, an atomic nuclei can be described in terms of the energy of binding of a molecule of a nuclei can be described in terms of an expression, the empirical expression found at the beginning of the 1930s, 1940s, involving surface and volume and column terms. And this liquid model of the atomic nuclei just required a small number of parameters, just four parameters, to give the energy of any, the binding energy of any nuclei. If you use the total number of nucleons and the number of protons and these constants. This was a very famous formula, and here is the description of this semi-empirical formula compared to the real results. This point made that the people that were working with the description of nuclei from first principles try to get this formula from Schrödinger equation and terms that describe the strong force, and it was very difficult, but of course they got it in terms of but notice that the point is that one is using the same ideas one would use to describe a classical droplet in terms of the parameters of a very quantum system that corresponds to the nucleons in a nuclei. This formula nowadays, many years afterwards, it is also being used to describe the dynamics of nuclei. And in fact, it can be, there are calculations that describe excitations of nuclei using a liquid model, okay? Here you have a nuclei, it deforms, and it can take this shape and then break, giving rise to fission, okay? Another example of a quantum droplet corresponds to superfluid helium. In this case, you have a system that is, in fact, a fluid, a liquid, and in this case, for helium, if you are at very low temperature, this system, this liquid helium, acquires a quantum property that is superfluidity. It's a state of matter in which the fluid, the liquid, behaves like if it had no zero viscosity. Okay. In this case, the quantum droplet requires a temperature of about 2.7 Kelvin degrees, and it is indispensable to take into account the bosonic character, that is the tendency of the constituents of the liquid to try to stay in the lowest energy state to understand this behavior, okay? When a quantum droplet is excited, you can do it in a symmetric or just working with the surface of the system or with the entire system as a whole, and you will find in general that there is a minimum energy to excite the condensate. That corresponds to the concept of energy gap. You can also try to make the liquid to rotate, and it is well known that in this case, the liquid will not rotate above a critical rotational speed, and otherwise it will try to use the energy creating vortices inside the they are using these drops of helium to study chemical reactions nearby this superfluid. The results are very interesting. Unfortunately, I will not talk about them in this talk, but they are really related to quantum chemistry nearby a superfluid with very, very impressive results considering single atoms nearby such a droplet. And one finds that the chemical reactions facilitate binary encounters and absorbs the binding energy release in a chemical system that is, in this case, it is more than a chemical reaction. Is you have a cesium atom, you send light, you ionize this atom, and it will have a tendency to recover, to reabsorb, recombine. And this recombination will be faster if it is close to a helium droplet. Okay. Now, what I have been doing during the last 2 or 3 years, no, four, I have been working on quantum droplets of atomic Bose condensates, but not considering helium, but considering other kind of gases, that is non-inert gases. In this case, I will work with BECs from alkaline atomic gases. And for the description of this system, I will consider the interaction between the atoms. But to get droplets, it is necessary to go beyond the mean field approximation. My contribution in this work is the identification of the surface tension and to show that the definition, the proper definition or characterization of the surface tension of these quantum droplets gives rise to the proper description of collisions of these droplets, and even to the proper description of the formation of vortices in quantum droplets. In general, Bose-Einstein condensates of alkaline or of molecules or anything that is not an helium, an inert gas, is carried out in the laboratories quite frequently. Now it is standard by this mechanism. One is first send light to the system to be cooled using Doppler cooling. Then it goes to a magnetic slower, that is a system that makes the atoms move slow, very slow, using magnetic fields. Later on, it is collected in a optical molasses, and finally, evaporative cooling is carried out. I must mention that here in the Instituto de Física, we have the only laboratory in Mexico that has gotten a BEC condensate, and in fact, this is the only BEC condensate formed from these condensates are generated both for fermionic and bosonic systems, that is, they generate Fermi gases or BECs, and I want to say that because we're very proud of it. Now, when you have a Bose-Einstein condensate, you have a system where the atoms move very, very slowly, so that the de Broglie wave of the movement, the center of mass movement, is very big compared to the structure of the potential that describes exactly the interaction between the constituents. This leads to a description of with pseudo potentials that are very, very practical, and that codify all the important properties of a condensate. These pseudopotentials were studied by Fermi in the 30s to describe atomic gases, and the interaction is simply described by a contact interaction with a parameter that depends on the relative mass of the particles that are colliding, and a parameter called the scattering length. So this system, one could expect that a BEC of an alkali atom can be very complicated, but at the end, the correct description of the collective behavior of the system requires just a simple, very, very simple parameters that, in fact, can be controlled in the laboratory, that is the scattering length. If the scattering length is negative and you have a Bose-Einstein condensate, this system will be unstable. If the scattering length is 0, you have a non-interacting gas. And if alpha, if this parameter is greater than 0, you get unstable BC because you get a minima in the effective interaction. I must mention once and many times that one of the most important points about BECs and the usefulness for the simulating and other systems is that it's a system where the interaction is controlled in the lab, contrary to what happens in solid-state systems or any other system where Coulomb interaction depends on the particles and you have to live with that fact. In this case, you modify the interaction by means of external magnetic fields. That is, you have control of the scattering length, and this control is fundamental. Okay? Now, I want to study droplets in BEC system, and so I have to write the equation of the system. If you have a system that is interacting with itself by means of a contact interaction, then you expect that the effective potential depends on the product of the density and the wave functions. Here, that is the Gross-Pitayevsky equation, and here I have writing it. If you consider just a single kind of atoms forming the system, this expression, as I told you, can give rise to BECs or not, depending on the sign of this of the scattering length. Okay. In the lab, people can consider not just BECs with a single kind of atoms, but they can consider combinations of atoms, that is heteronuclear admixtures of atoms in the BEC. And in such a case, there are different regimes. That is, the two kinds of atoms can be close to each other if they are of the same species, and the other species entangled with them in the density, or they can be separated and they can be those do not mix completely. And this is an experimental showing that. Okay, now I want droplets, and it is impossible to get droplets if I work with a single species of atoms, because either it forms a condensate, but that requires, in fact, an external field to be self-confined, or if you have a mixture, but you consider any value of the parameters that describe the interaction, not always you will be able to get a droplet. Okay? 10 years ago, it was shown that for systems where fluctuations are important, that is beyond the mean field approximation, it is possible to get droplets if you have the proper choosing of the atoms and of the scattering length that combines them. If you have a mixture of atoms and you have fluctuations in the density of these atoms, and these fluctuations are due to collisions between the particles where they just interchange the momenta. One goes in one direction, one and to the other. One works with what is called the Li-Huang-Yang theory, and the extended Gross-Pitayevsky equation. In this case, the mean field terms that go with the square of the density, that is this, multiplied by this, and it's calculated the density, the square of the density. These terms can be chosen to be go to n to the square, the Liouville terms go like n to the 5 to this power. And if they are negative and these are positive, there will be a self-trapping regime, so that you will have a gas that becomes a droplet if and you don't require an external field to create it. This point was predicted, as I told you, by Petrov 10 years ago, and he gave the general parameter, the scattering length, the relations between the scattering length between the atoms of the same species and of different species, and showed that if you have this condition, you will be able to get a system where both species mix, they are not separated, and they produce a droplet. The general parameters of social droplet were predicted by Petrov in this very, very nice work. And he also gave other important parameters like the saturation density. That is how when you add more and more atoms to the system, there will be a moment that the density will saturate, and the other atoms will go to the borders, and some will go to the center of the wave. Okay. The experiment to observe the first quantum droplet was done by a Mexican. It is Cesar Cabrera, that was working with Laura Taurel in Spain. And yes, in 3 years after Petrov, this Mexican guy that is very, very good experimentalist, and unfortunately he's now working in Germany, and I hope he will come back someday because it's spectacular. He got in his PhD thesis, under the direction of Laura, the production of self-trapped system that is quantum droplets with control properties. Later on, some experiments had been carried out in Italy and other places, but these were the first ones, and the first was done by Cesar. Okay? Then, what have we done? What we have done is making the numerical description of the system. We have been able to calculate the ground state of the system by using a standard, well, not trivial, but standard numerical means. And here I am plotting the results. And for me, in terms of the subject of this talk, it is very important to notice the shape of the density of this system. If you have to say 5 to 10 to the 5 atoms, in such a case, you get this form to the density. Okay, density normalized to unity. Okay, if you add more particles, this shape is modified to this, where all the atoms in this case share a density, while the other atoms are at the borders. And as you add more and more atoms, the density is flatter and flatter up to the borders. Okay? In our calculations, we were able to study and to parameterize this skin, the skin of the droplet, the radius of the droplet, using experimental parameters. And this is what we found. Okay? Now, what we wanted to study was not only the ground state, but we wanted also to study the excitation of the droplet. In such a case, it is necessary to use we decided to use the Bogoliubov, the Jens formalisms, that allows to study the excitations whenever they are harmonics. So you have a droplet with an energy that in this case is identified as the energy required to add more particles to the system, that is the fugacity. And here you have the frequency of possible excitations. These frequencies can be with positive or negative evolution on time, and the calculations are of this frequency can be carried out in terms of the exact solutions of the excitations. What we did was to consider a variational theorem established by Fowles that allows to get approximation to the time-dependent problem, and that is the title of my talk, considering a time-dependent problem to describe and use this theorem to give a good description of the excitations of the droplets when you hit them or collide with them or anything like that. This theorem requires that you give an ansatz for these functions. That is, you say, okay, I don't know the exact form of the... And given the ansatz, you calculate the different, then the effective energy or the frequency in terms of this expression, okay? And look whether or not, what is the value you get, and you know that your ansatz will always give a greater value than the exact one, okay? In this case, we consider that the initial droplet was spherical, assume that the excitations had this form. Since it was spherical, the functions we use involve the spherical symmetry system, and consider two kinds of ansatz, okay? Consider different ansatz gave us different values for the energy of the system, and we calculate this result for rubidium and rubidium mixed with potassium, experimental parameters, extended Gross-Pitayevsky's equation, compared with some phenomenological prediction of Petrov and some Monte Carlo calculations of the systems that do not use the scattering rate, but effective interaction between all the molecules. And our results were quite nicely compared to the Monte Carlo calculations and to Petrov calculations, but they depended on the ansatz of the system we use for the system. And here I put with continuous line the ansatz one, and with continuous lines for the second ansatz, and dashed line for the first ansatz. And we see that depending on the number of particles, one ansatz gives a lower value for omega, while another ansatz can be better for a different region of n. What we found is that this region of n corresponds to a compressible liquid, and this region corresponds to an incompressible fluid. So the different ansatz are better for different regions, and in general are better than predictions of the Petrov result and comparable to the Monte Carlo results. This is just showing our calculations in logarithmic scale to see the difference. Okay. Once you have an expression for the excitations and for the behavior of the system, one can ask what is the value of the surface tension. I must tell you that this calculation and this inspiration of the ansatz that we use and everything can be traced back to Lord Rayleigh. We read the original paper of Rayleigh in 1879, where he introduces the concept of surface tension, and he also introduces the variational approach to the description of a fluid that is now what we use in quantum mechanics to make variational calculations. That is, the Rayleigh-Ritz method was introduced to describe the excitation of droplets. And in this paper, Lord Rayleigh, that was a genius on Doppler, also introduced the concept of surface tension and gave the description in terms of the angular momentum of the excitation with an explicit expression in 1879. That is impressive, okay? Now, more than 150, almost 150 years later, we have done that for a quantum droplet, and using the definition of the surface tension, we were able to calculate it both for Ansatz 1 and Ansatz 2, and those gave an explicit expression for the surface tension of the system depending on the regime. How that this result can be shown to be useful? Then you have to give an excitation mechanism, and the excitation mechanism we chose was the collision of two droplets. So we describe a droplet, then make the collision of the droplets, make the numerical simulation of the time-dependent Gross-Pitayevsky equation, extended Gross-Pitayevsky equation, and calculated how two droplets collide. Use also our definition of the surface tension, use a calculation of the translational kinetic energy that the system has, and like the people do in fluids, define the Weber number. The Weber number is the difference, the ratio, between the energy you have when two drops are translating one towards each other, compared to the energy you require to break the surface, to do something to the surface. Here are the results of our simulations. You have two droplets. They approach each other, collide, and then many things could happen depending on the size of the droplet, the energy of the droplets when they collide. And I want you to see that the things we are looking here are very similar to what happened when two atoms, when a nuclei is excited. Imagine that this is an original nuclei and become excited, and then it can, if you see the reversible, if this were a reversible system, you would say that you have an excitation, and then a fission of the system. So this kind of calculations are very similar to what they do with nuclei, but here we are considering more fusion than fission. No? Our calculations were compared to some experiments that were done just at the beginning of the studies of quantum droplets in liquids and in BECs, and the results were qualitatively equivalent. So we were happy because our calculations are okay. Our definition of the surface tension in terms of the system is okay, and the only thing that remained to be done was to consider the diagram depending on the parameters of the system, that is the number, the kinetic energy of the system, the number of particles that are involved, and to see whether or not when two droplets collide, they coalescence or not, they remain close to each other, forming a new bigger droplet, or when they just dissociate, or when nothing like this happens. And our calculations were okay, and we saw many interesting results that I will just mention a few of them. For instance, in this case, two droplets approach to each other and form a bigger droplet. What is true that if the droplet has the bigger droplets, or the smaller, the bigger droplet corresponds to a region where the chemical potential is lower than the energy to evaporate, then the bigger droplet will evaporate. And we were able to predict that. And we also consider a very important fact, that is that the systems, the atoms that are inside the droplet, may get out of the BEC regime because three-body collisions give rise to atom losses. This was also introduced in our calculations, and here I'm showing the results. Finally, I want to open question for quantum information theory. In all the calculations I have shown to you correspond to calculating densities, and of course I am able, without any problem, to calculate the Shannon entropy of the systems, since I am very happy with the numerical results I get. Without doing any calculations, I can say that this quantity will be important for me. Why? Because when I am in the regime where a saturation density arises, I know that the density will be a constant during a important region of measure different from zero of the space. So this logarithm that can be taken as normalized to the saturation density will be a constant during a very long region, and so it becomes something I can get out. And only in the region where you have a skin of the liquid, in such a region, the entropy will be relevant. So the system, just because of its definition and because of the structure of a liquid, will have the relevant information from the point of view of Shannon entropy will correspond to the skin of the droplet. And that, of course, is logical because the density inside the droplet is constant. It is boring. It gives you know everything about it. It gives you no information. But when you are at the skin, all the information that is relevant, all your ignorance is evident, so information is there. And if you apply Shannon entropy, of course, this quantity gives you about information of what happened in the skin, and what happened in the skin is obviously related to the surface tension. So for the ground state solution of the Grothendieck equation, it is clear that this information will be important, that the Shannon entropy gives you information. And when you have excited states of the quantum droplets, and you are also in the incompressible regime, this will tell you also that the surface that in such a case will not be spherical, will have the shape determined by the system, will be also the only region that is relevant to you. Okay? Of course, the system is quite complicated because the number of particles that participate in the condensate depends on time. In this case, the problem of self-evaporation will give rise to a system where the density is not something that can be normalized to unity all time, but it will be a quantity that depends on time. And this is a source for more information. How many particles are lost? And this depends on the normalization of rho that cannot be 1 because some of the atoms are going out. The system is open. The atoms are going out. And something similar occurs with the three-body scattering. Finally, the fact that we use Bogoliubov-de-Gennes formalisms to describe excitations makes clear that it is important to understand time-dependent problems from the point of view, time-dependent problems either used for quantum field theory or for the quantum description of something like a droplet. It is important to understand how much information is carried out in terms of the natural description of the system. The Bogoliubov-de-Gennes formalism, what it does is describing the excitations in terms of the U and V functions that are the natural description of the system, But it's not the only description you can do. You can also do social description using other functions. So this, the Bogoliubov transformations identifies the proper basis for the description of the system, and that is also information. Finally, the Fowler's variational theorem is based on the stability of the many body ground state of both bosonic and fermionic system. In fact, Towles and Birch, that is a very important person for the nuclear community, established such a theorem both for fermionic system. They wanted to describe the drop model of the drop model for nuclei, and so they use fermionic and bosonic system. And this theorem is a quantum theorem, but I have never seen, if someone knows of it, please let me know. Otherwise, it would be a very interesting problem to deal, is whether or not this variational theorem can also be understood as an extreme value of a quantum information measure that depends on time. In the case of one is working with excitations, periodic excitation of the system, is it possible to establish an extreme value of quantum information? In this case, that is the physical excitations, the available physical excitations corresponds to extreme values of the quantum channel theory. And these are open questions that I haven't answered, but I think that could be important. These others, I am not giving you the numbers, but you can see that it is clear that the Shannon theory entropy is a natural language for describing the droplet, because when they go directly to the interesting regions of phase, maximize the interesting regions of the systems, but the time evolution requires working a little bit more. And I want to thank you for your patience, in particular because of all the problems I had at the beginning, and thank you very much to the organizers.
Thank you, Rocío. There are 2 minutes for questions. If somebody has questions or comments, please. Well, if there is no comments, no questions, we thank Rocío again and all the speakers in this session. Thank you very much. We will resume we have the lunch break, and we will resume at 4:00 p.m. Thank you,
Roberto.
much.
Have a nice day.
Thank you, Rocío. Bye.